Good morning, everyone. I apologize for the delay. A gentle reminder to all our participants to mute audio and keep the video off for the session. I, Sneha Taishete, on behalf of IEAR, warmly welcome all our participants and our speakers today. Today's program, Valuing Our Water Resources, on the occasion of World Water Day, is organized by Institute of Environmental Architecture and Research, IEAR, in collaboration with Water and Land Management Program, Department of Civil Engineering, Visvesvaraya Technological University, VTU, Belagavi, Karnataka. The Institute of Environmental Architecture and Research is a Mumbai-based educational research and training institute with a vision to create a sustainable environment through scientific research, education and training, socio-cultural understanding, community engagement, and awareness. We are a multidisciplinary group of scientists, professionals, and academicians who have joined forces to form this organization, having worked collaboratively for more than 15 years on education, environment consultancy, and awareness. Our mission is Environment First. This is the 19th webinar in the series, which we started during the lockdown period. So far, we have reached out to more than 2,500 participants altogether from around the world. Our main objective in this webinar series is to provide educational and research inputs and a scientific and analytical approach to environmental issues. VTU, Visvesvaraya Technological University, Belagavi, is named after Bharat Ratna Sir M. Visvesvaraya and is established in the year 1998 by Government of Karnataka. This university has many affiliated colleges, a constituent college, and 17 autonomous colleges with undergraduate courses in PG programs and PhD and MSc engineering with research programs. Over 4 lakhs engineering students study in these various institutes affiliated by the university. VT introduced water and land management program in the year 2011 to prepare specialists to address the challenges related to water and land resources. This program is an integration of environmental engineering, water resource engineering, and geospatial technology. On the occasion of World Water Day, let's celebrate water and raise awareness about the significance of this important element. As climate change melts glaciers and threatens food security and agriculture of our subcontinent, even as coastal inundation progresses, valuing our water resources become vital. With this context, we begin our one-day international symposium on valuing our water resources. I would now like to introduce Dr. Roshni Udyauri Yahuda, President of IEAR. Dr. Roshni Yahuda is a practicing architect and an academician. Her core competency lies in energy efficient and environmental design of buildings. Dr. Roshni was the head of Rachna Sans's Institute of Environmental Architecture from June 2003 to July 2017, where she initiated several water conservation projects such as the Dahisar River Restoration, Charlotte Lake Revitalization, and Mankud Slums Drainage Improvement projects. She also commenced national level annual rainwater harvesting competition, Harvest to Harness, the first of its kind, in collaboration with the Times Foundation, Eureka Forbes Institute of Environmental Notices from 2004 to 2008. She has undertaken water audits, designed and commissioned rainwater harvesting for residential and institutional projects, Jezuri Lake Restoration, and Indapur Township water planning through Enviro Arch and through Roshni Udyawar and Associates. Dr. Roshni is co-chairman, Assocham GEM Maharashtra chapter. She is the advisor, Environment and Sustainability, Science and Technological Park, Pune. She is the principal investigator for the Department of Science and Technology, Government of India's research project on developing energy efficiency and ECVC compliant opaque wall assembly, and member of the board of Town and Country Planning of the All India Council of Technical Education, AICTE. She has more than 20 years of academic and professional experience and has traveled widely on professional assignments to more than 20 countries. I now welcome Dr. Roshni Yahuda, President of IEAR, to take over this meeting. Thank you.
Thank you, Sneha. And a warm good morning and a warm welcome to all our experts and speakers of today, faculty and students of IEAR, of VTU, and members, trustees of IEAR, Dr. Shivapur, Chairman of the Civil Engineering Department, Professor Rohan Gura, and all the participants. Good morning and a warm welcome to all of you. The theme of our symposium today on the occasion of World Water Day is valuing our water resources, which is in line with the United Nations theme for this year, 2021. Water, as you know, is the most important resource available to us, and yet its value as a resource goes beyond its price as it significantly influences our lives. Without water in the form of rains, we would have no agriculture, no food. As we know, most of agriculture in India is rain-fed. And the many freshwater rivers that flow on the surface have been the cradles of civilization, not just here in India, but all over the world as we know it. The glaciers that are the source of mighty rivers, such as the Ganges. Then we have the groundwater, which we extract through wells, bore wells, tube wells, and of course the oceans that cover 70% of our planet, or for that matter, our bodies, which are 60 to 70% water. Water is deeply entrenched into our culture and traditional practices, our lifestyle, and it is an integral part of the living world. Yet, with so much water available, we know that less than 1% of this Earth's fresh water is actually accessible to us. Despite all this, we have not done much to safeguard this resource. More than 80% of the world's wastewater flows back into the environment without being treated or reused, according to the United Nations. In some least developed countries, as they call it, this figure goes up to even 95%. So we are polluting our rivers, our freshwater bodies, and our oceans. And we can see this all around us. Almost in every Indian city, the rivers that we see in the urban areas, mostly downstream, are polluted. And in many cities like Bangalore, for example, the lakes, Bangalore was a city of lakes, but these lakes have been rampantly polluted or even built over with least consideration for the ecosystem or the hydrology. And as a consequence of all this that we have done, nearly 780 million people today are without access to clean water. That's roughly 1 in 10 people on the earth. Now, climate change is also affecting the whole scenario with respect to water. And one of the things that is happening is in the increasing intensity of precipitation, as was predicted originally in the in 100 years or so, there are floods being witnessed in Australia, and that is definitely a result of the you know the intensity of rainfall increasing, and many others like melting of glaciers that is threatening the very rivers which are the lifeline of our civilization and society. And what we are seeing is also that everywhere the effects and the impacts of climate change are being felt by the poor and the marginalized, the economically marginalized. The worst brunt of the impact of climate change, such as sea level rise and storm surges, are being felt by the poor and the marginalized. So with this background, I think we have a wonderful panel of speakers today. We have, I would say, the most authoritative speakers present with us for this international symposium. Of course, Neha will be introducing them, but briefly, let me just tell you a little bit about them. Dr. Ravi Chopra, former director of the People's Science Institute and chairman of the high-powered committee appointed by the Supreme Court of India to review the Char Dham Pariyojana in Uttarakhand. He will enlighten us about what is happening with Himalayan rivers. I'm very much looking forward to hearing him, and I want to thank him for agreeing to be present here for the symposium despite his very difficult time commitments. We will also be shortly joined by Mr. Avraham Israeli, the past president of the Israel Water Association. He will talk about the Israel water experience from shortage to water sufficient supply. Indeed, that is one country which has shown the world how to value water and make the most of it through technology, through research and development, and through genuine efforts towards solving people's problems. Then we have architect Nandan Mungekar. I can call him the father of rainwater harvesting because I think more than 15 years ago, when nobody even knew what was rainwater harvesting, he was not just preaching but also practicing it. So we will have the pleasure of seeing some of his major projects and also all the knowledge that he will share about his experience with all these projects. And last but not the least, we have from Berlin, Anjali Butner, an engineer who has dedicated herself to the practice of green and blue infrastructure. You must be wondering what this is, and you should wait till the very end to hear her. But I would say that she is making extraordinary efforts as a designer, as an engineer, and a project manager to replace the concrete and the hard surfaces that we have poured into the ground over the years in the name of urbanization and development. And she's replacing them with vegetation and water that is green and blue. So this galaxy of speakers will enlighten us today with technological solutions, with methods and techniques in order to revive, restore, and conserve water, whether it is in agriculture, in rural areas, or urban ecosystems. I urge everyone to make notes, listen, feel free to ask questions because we want a good, lively discussion. We have kept time after every talk for discussions. So please post your questions in the chat box on Zoom or put comments on the Facebook page and make the most of the expertise of these speakers who are there here with us today. Believe me, we are indeed privileged in this short duration of a day-long symposium to absorb the wealth of knowledge that they will be sharing with us today. So with that, I hand over back to Sneha. I think I again welcome all of you and hope that we learn and take this knowledge and apply it and use it for the future. Thank you. Over to you,
Thank
Sneha.
you. Thank you, Dr. Rashni Yadav. I would now like to introduce Dr. Anand Shivapur. Dr. Shivapur is the chairman, civil engineer. Just a moment. I'll get back to you on that. Dr. Shivapur is the chairman, Civil Engineering Department, Visvesvaraya Technological University, Belagavi. He holds a PhD degree in civil engineering, an ME degree in hydraulics, and a BE degree in civil engineering. Dr. Shivapur has been associated with VTU since 2013 as the professor with hydraulics, which is his area of specialization. He has been a research guide for many PhD candidates. As a professional, his R&D project on analysis of flow over inclined weirs of simple geometric shapes, sponsored by AICTE New Delhi for the period 2003 to 2006, received a grant of 1.92 lakhs. He has over 43 papers published in national and international journals and has contributed to over 7 books. He has more than 35 years of experience as an academician and environmental consultant. I warmly welcome Dr. Shivapur for his presidential address. Over to you, Dr. Shivapur.
Thank you, madam. Am I audible now?
Yes, sir.
And everyone present here. Good morning to all the participants, the speakers, and my dear colleagues. It's indeed a great pleasure to be associated with the institution, Institute of Environmental Architecture and Research, Mumbai. We have jointly organized this international symposium on the World Water Day. Dear friends, today we are all here assembled to celebrate the World Water Day on this day of 22nd March 2021. In fact, as you all know, the World Water Day has been started in 1992 at Rio de Janeiro United Nations Conference on Environment and Development. And the day on which a decision was taken to hold the World Water Day every year on 22nd of March every year. And as you all know, that we are today holding a 28th World Water Day with the main intention to put a discussion on the world water conservation sustainable use. So in fact, there are 17 sustainable development goals that United Nations has made. Out of this, the 16th sustainable development goal, which is the sustainable development goal on water and sanitation for everyone. This is basically to ensure the access to water and sanitation to everyone by 2030 is the main aim of the 16th Sustainable Development Goal of United Nations. Dear members, as you all know, Madam has already told, 71% of the world water, 71% of the earth has been covered by water. Yet only we have only 1% of the fresh water available to the people now. And at the same time, you know that 60% of human body contains water. So that is the essence of water everywhere. The main theme of this year's World Water Day is valuing water. In fact, we are celebrating this with valuing our water resources. When it comes to valuing water, water means different for different people. What water means? How is water important to your home and your family life, your livelihood, your cultural practices, your well-being, your local environment? Everything is covered. Valuing water is different for different people. The agriculture looks at differently, the farmer looks at it differently, and a homemaker looks at differently, and a student looks at in different way, and a teacher looks at a different way, economist looks at different way. So, and biodiversity engineer looks at different angle, and sustainable environmentalist looks at a different way. Environmental engineers looks at water in valuing water in a different way. So for everyone, water looks different. Every drop of water counts. Even in agriculture, we say a drop of water will. The aim of agriculture is to grow more water for each drop. So this being the issue, and in the present scenario, the climate is undergoing tremendous change. Climate change is the main issue today. Because of this, we often get droughts, we often experience the deficit irrigation and control in different agricultural practices also. So water is a main issue, and when it comes to a river, a lot of river, 80% of the rivers are getting polluted now. So most of the civilization, as you look at in the history, is on the banks of the rivers. They are in search of water for their livelihood. That is the reason why most of the civilization has started very close to the river banks. Today, this most useful water has turns out to be the most dangerous sometimes. So useful water becomes dangerous many times, and this water which is available to the people who are residing on the banks of the rivers makes the river water polluted. Because of this, downstream people get affected because the lack of quality of water which is required for their domestic purpose, for agriculture purpose, for many other purposes. So issue of water and issue of sanitation are the two mainstreams which are basically worrying the engineers and economists, even educationists also. So the aim of this year is to identify where the pitfalls are for making this environment sustainable. So in that direction, we are making one effort to educate the people, to make them to know the technology, make them to understand the issues connected with water and sanitation and environment. So we have today with us four prominent speakers, and Ravi Chopra is known for his work on water. Basically, he is now more concentrating on Himalayan rivers and their quality, and he'll be with us sharing his ideas. And there's a person from Israel who happens to be associated with the Israel Water Association, who briefs about the techniques used for maintaining the water quality. And we also have Nandan Mungekar, who is known for rainwater harvesting the last so many years. He is with us, and we will be talking on rainwater harvesting today. Most of the techniques and the benefits of rainwater harvesting will be speaking on. Then we have with us the well-known engineer, identified engineer, who is known for clean and blue infrastructure. So Anjali Butler, she will be speaking on water management in urban areas. I think with this effort, we make a move towards understanding the water and valuing of water, basically with an interest to ensure that water is available for everyone and to maintain the sanitation in and around us. With this, I am sure that the participants will get a lot of knowledge through these different lectures given by the people around the world, and will be able to make some outcome from this and suggest suitable measures to ensure we can be able to achieve sustainable environment in the world. Thank you, ma'am. With this, I once again wish all the participants to make a notes and then put your questions before the experts and get to know more about the valuing of water. Thank you, ma'am.
Thank you, Dr. Shivapur. I would now like to welcome Dr. Ravi Chopra. Dr. Ravi Chopra is the chairman of a high-powered committee appointed by the Supreme Court of India to review the Char Dham Pariyojana in Uttarakhand and former director of People's Science Institute. He did his doctoral research at Stevens Institute of Technology, New Jersey. He is a recipient of IIT Bombay's 2012 Distinguished Alumnus Award. In 2013-14, Dr. Chopra chaired an experts body appointed on an order of the Supreme Court to examine the environmental damage caused by hydropower dams in Uttarakhand. From 2009 to 2013, he was an expert member of the National Ganga River Basin Authority, chaired by the then Prime Minister, Dr. Manmohan Singh. His present research interests are focused on India's water requirements in the 21st century and the sustainable regeneration of Himalayan springs and rivers. He is currently co-editing a citizen's report on the state of River Ganga. Dr. Chopra has worked for over 5 decades in the field of development and has helped establish several pioneering organizations. The issues addressed by them include involving youth in India's development, using science and technology for empowering the poor, protection of democratic and human rights, rehabilitating survivors of natural and human or man-made disasters, and creative education of children, including the mentally handicapped. I welcome Dr. Chopra as our first speaker for his keynote address. Over to you, sir.
Thank you, Sneha. Can you hear me?
Yes, sir.
Good morning, everybody. Distinguished guests and participants, I'm delighted to be here today to share with you many of the lessons that I have learned from the Himalayas from the rivers, and lots of people across the land. Let's start the slideshow. I'll be talking almost exclusively about Himalayan rivers today. The first slide that you are seeing on the screen is the source of the Bhagirathi, one of the two major headwater streams that feeds the Ganga. And this is Gaumukh, about 10 years ago. The picture on the right is the Ganga Brahmaputra basin. It covers about 43% of India's area. And about 600 million people are currently living in this region. These two rivers account for almost 66% of India's annual surface flows. I think that figure should be for three rivers, Indus, Ganga, and Brahmaputra. Okay. It is not well appreciated that this region is a highly biodiverse region, which I have chosen to represent in the form of the tremendous animal and plant life. You can see some very rare species here, from the snow leopard on your left, the rhinoceros, monal pheasant, golden mahseer, there's the Brahm Kamal in the middle, and the gharials on the lower left. The Himalayan rivers are broadly of two types. There are the glacial rivers, like the Pindar on the left, comes from the Pindari Glacier. An important characteristic of the glacial rivers is that their winter season flows are very low because the glaciers are frozen. But there are many more springs-fed rivers, like the Western Ram Ganga in the right-hand picture. Here, the lean season for the flows is in summer. Very often there is a mistaken notion that the Himalayan rivers, North Indian rivers, are full of water because of the glaciers. That's actually not true. Even though we have almost 10,000 glaciers in the Indian Himalaya, their contribution to the annual water flow is quite low. Even at a place like Dev, where the Bhagirathi on the left meets the Alaknanda on the right to form the Ganga River, the annual contribution of the glaciers is only 27%. And by the time the river reaches the ocean, I doubt if the glacial contribution is even 2%. Okay. Now, very often when engineers look at a river, they see only the water. But rivers are ecosystems. They contain water. They contain lots of sediments. And in the case of the Himalayan rivers, since they are draining tectonically active regions, their sediment load is huge. The Ganga Brahmaputra system brings about 1 billion tons of sediments every year to the Bay of Bengal, and that is the heaviest sediment load anywhere in the world. One small river, the Kosi that comes from Nepal, if you were to take the silt of this river, convert it into a wall with a cross section of 1 meter by 1 meter, you can go around the equator 2.5 times. Now, most of us are aware that Ganga Jal does not putrefy. And this unique self-purifying capacity is due to the same sediments that the rivers bring from the high mountains. Most of the Himalayan rivers have this very high self-purifying capacity, but none as much as the Ganga. The graph on the right will show you that in the Ganga, you can reduce the coliform count to below 1% in about a day. Whereas similar measurements done on American rivers, the time taken is 4 to 7 days. Much of the water that flows in our rivers is actually base flows, the rainwater that trickles down into the river valleys through the mountains. India is the biggest user of groundwater anywhere in the world, and this is leading to severe groundwater depletion in the Indo-Gangetic plains. In fact, a study done at IIT Kharagpur showed that in the 45-year period from around 71 to 2016, base flows into the Ganga, into the lower Ganga, had declined by about 60%. Now, the entire Himalayan region, people living in the villages and towns are not so dependent on the big rivers for their daily water needs. For that, they depend on the groundwater flows, whether it is in the form of a spring, as you see on the left, or it is in the form of a step well, shallow step well. The amusing thing is that until about 10 or 12 years ago, the Central Groundwater Board never acknowledged the presence of groundwater in the mountains. But these discharges are decreasing in recent decades. Long period of deforestation in the mountains and the changing species diversity of the plants has led to a very steady decline. This is a small river called Kosi in Uttarakhand. It flows by Almora. And as you can see the hydrograph on the right, which is the summertime measurement recorded every year at the same spot, you can see that in 1994, the river discharge was almost 1,000 liters per second. And by 2004, it has come down to around 100 to 200 liters per second. A massive decline. And this is what is leading to the decline in water flows in the rivers downstream. Now, to give you an example, here is a small stream that feeds the Kosi River. This stream, this picture that you see is 1991. And you can see that the small stream, which we call Khulgar is fed by a number of first order and second order streams. Now watch what happens in 2004. Almost all the streams have dried up. There's only a small stretch of Khulgar left to feed into the Kosi River. Most of us, when we read the newspapers, we read much more about the pollution in our rivers rather than the flows in the rivers. Now here you can see the inset. The inset is the Yamuna River in the Himalayan region. And by the side of the beautiful Taj Mahal, this is the state of the Yamuna River, full of debris thrown by people. And of course, scenes like this have been splashed all over the media in the last almost a decade. And the Ganga pollution continues almost unabated. But as I said, far more important than the pollution levels is the flows in the river itself. And a major impediment to the flows in the river are the dams that we have constructed on them. Now, 70% of India's hydropower potential is in the Himalayan region. The Himalayan states do not have too many sources of revenue, so most of them have been on a dam building spree in the last 15 or 20 years. This is the Teri Dam that you all may have heard about. It has a huge 42 square kilometer reservoir behind it. This is a map of hydropower locations in Uttarakhand, and I have been able to show only about 240 odd locations here, as opposed to the 450 that are planned or built so far. What you might see is that there are two stretches that I have marked in yellow. And the yellow line on the right-hand side is the Gori Ganga River. It's a small 72-kilometer long river, comes from a glacier, and there are 7 dams on it. So every 10 kilometers or so, you have a dam on the Gori Ganga. The yellow line on the left is the Bhagirathi. And shown on that are a number of projects, some of which have been fortunately cancelled in the recent past because of people's protests. Now, what happens when we build these dams? As you all recall, in the 1980s, there were these 2 big protests against the Narmada and the Teri Dam. And thereafter, engineers decided not to build too many storage reservoirs, large dams, but to build barrages on the rivers. And in a barrage, you may take you can see on the top right-hand side, there is the intake on the right-hand side. You take the water from the river, you push it into a tunnel which goes along the mountain contour, and you release it 5, 10, 15, 20, 25 kilometers downstream at a powerhouse. The stretch between the dam and the powerhouse usually goes dry because the engineers don't want to release even a drop of water to the river. They don't see the river as an ecosystem. For them, it is water. That's what happens. On the left, you see the beautiful Alaknanda as it comes down from around Badrinath. And it's a beautiful, lively river. And on the right-hand side, it's downstream of the first dam on the river. That is the Vishnuprayag hydroelectric project. And the bed of the river is almost dry. And this is not unusual. Watch what happens to the Bhagirathi. The Bhagirathi, again, is a nice broad river around the village of Maneri. And by the time it comes down to the Uttarkashi town, there's the Maneri Bhali 2 project. And downstream of the Maneri Bhali 2 project, there is almost no flow. And this is the situation almost around the year. Now, there are a lot of problems that begin with the pre-construction phase when we have to make roads to take equipment to the dam site, and lots of trees are cut down. Then there are problems in the construction phase, as shown in this picture. When we construct dams, unfortunately, we're not very mindful of what happens to the river. The muck from the tunnels is just pushed down the slope and it ends up in the river. Now, when it ends up in the river, then it makes the water turbid, the sunlight cannot penetrate, and lots of organisms that live on the bed of the river, they need that sunlight to manufacture their food, and they die out. Now, in this picture, I've shown what happens to a particular family, the Plecoptera families in the Bhagirathi River. This is, I think, the data for the Maneri Bhali 1 project. And you'll see that at the bottom panel is the reference station. If you look at the reservoir, there's almost no family left. The density is down to 0. And that is because the reservoir is deep. The water becomes turbid after a while. There may be algal growth, and then very little sunshine will penetrate to the bottom. But as the water is released down the outlet or down the powerhouse, then the organisms begin to revive again, but not to the reference station level. We've done some measurements on the self-purifying capacity of the Bhagirathi river. The curve at the top is from a reference station, and what we have done is we've added some sludge to about a liter of water, and we've watched how long it takes to settle down at the bottom of the bottle. And you can see that it takes about an hour for about 2 milliliters to settle down at the bottom. Okay, but next to that is the crimson line, which is downstream of the Maneri Valley project, and it has lost a lot of its self-purifying capacity. By the time it comes down to the Teri Dam, which is the blue line, it has lost 50% of its capacity, self-purifying capacity. But there are many more problems. In the construction of these dams, when we dig tunnels in the mountains, then we introduce new fissures and fractures, and these underground water paths often change. In this particular case, the picture, the spring has dried up. The pipe is totally dry. The village was dependent on it, and now they have no source of water for their village. Very often, when we first test the release of water from the tunnel to the powerhouse and it goes down the penstock, we've often seen that there are cases of land subsidence or landslides. Okay. Now, what happens when there's a landslide? You can see this. Infrastructure may get destroyed. There was a road at the bridge on the top, and it has fallen about 20 meters below. Okay, where my friend is standing. As the land slides or subsides, then there are tremendous problems of slope failure. And this scene is not of an earthquake, it is that of a landslide. This house has been hit by a landslide. We often see cracks in the fields, fissures in the fields. You can see that the entire slope has been affected, that the forests are gone, the trees are mowed down. In fact, the powerhouse structure also suffered in this particular case. But it's not that the problems end after the construction of the dam. They can continue even after the dam has been commissioned. This is another part of the Teri Dam reservoir. And what you see is that every year during the monsoon, the water fills up in the dam. And due to the hydrostatic pressure, the water enters into the surrounding slopes. As the water gets used and the water level in the reservoir falls, then the hydrostatic pressure is reduced. The water that had gone inside the mountain comes out. And when it comes out, it brings along with it tiny particles of soil to large rocks and small boulders. And you can see that the entire village above, the agricultural land above, is now threatened. About 4 years after the commissioning of the Teri Dam, the Supreme Court ordered the relocation of 27 villages in this area. And of course, when people are displaced, then there are protests. But in recent decades, we have a new problem, and that is the climate change, which Roshni referred to a little while ago. And she said that we are beginning to see more intense rain spells in fewer days. And that leads to this whole host of problems of floods, droughts, avalanches, etc., etc. You can read on the left, which affects the Himalayan rivers down to their mouth at the Bay of Bengal. The rising sea levels, coastal submergence are all dependent on the amount of sediments that come with the river. In this picture, a very well-known picture, you can see the recession of the Gangotri Glacier. Since 1935, it has retreated by about 1.5 kilometers. And a new threat which we are seeing is that because of the increasing density of motor vehicular traffic in the plains, the warm air with the particulate matter rises up to the glaciers in the Himalayas. And we are finding stretches of black soot, patches of black soot deposited on the mountain tops. There are sorties of helicopters taking tourists to places like Kedarnath, and that is all creating a whole new regime of pollution in these otherwise pristine areas. Now, here's what happens in the event of an extreme event. The region above about 2,000 meters, where the riverbed is at an elevation of more than 2,000 meters, in those valleys, we have paraglacial sediments. Sediments left behind by glaciers that have withdrawn in the last few thousand years. And there's a tremendous amount of debris, boulders, rocks, soil left behind. In the event of a massive rainstorm, as it happened in 2013, these are pictures from 2013, these small river streams that come from glaciers and feed the largest rivers, they are very destructive. And here's a small river called Khiroganga, which meets the Alaknanda River. And you can see that it has totally destroyed the Vishnu Prayag hydropower project on the right. The hydropower project is now totally covered with debris. Okay? And this is exactly what happened a few weeks ago in Chamoli district. February 5th and 6th, February 4th and 5th, there was heavy rainfall, there was snowfall. February 6th and 7th, there was bright sunshine. Because of the insolation, some of the snow melted. And when you have snow and ice mixing together on steep slopes, they can move very fast. And as they move downstream, they pick up all the sediments, the huge boulders, even if the boulder is about the size of a small room, it gets moved because the slope is very sharp. Remember that the feeder stream to the Rishi Ganga River came from about 5,000 meters height down to about 2,000 meters in a matter of minutes. And it converted all that potential energy of the water, rocks, and the ice, etc. When it hits the Rishi Ganga River at the bottom, it converts that into kinetic energy and pushes a huge mass of water. When this mass of water and sediments, boulders begins to move downstream, it has so much energy that will destroy almost anything in its path. So the first thing was a small bridge. Then there was the 13 megawatt project on the Rishi Ganga. And then it entered the Dholi Ganga Valley, where it saw the Tapovan Vishnugad project, 520 megawatts, and it destroyed that in a matter of minutes. The water being temporarily barricaded by the dam found another path towards the tunnel of the project. All the huge boulders blocked the tunnel. And then after the barrage had been broken, continued down into the larger Alaknanda Valley, where it knocked off several bridges, and finally 25-30 kilometers downstream from Joshimath, the river came as the bed slope became less steep. Okay, so this is what happens in a paraglacial zone. Here's an example of the Kedarnath image. 40 seconds, just bear with it. What you have just seen is actually a simulation. It's not the real event. Okay, so with all these things happening to our Himalayan rivers, what is to be done about all this? I think the first thing we need to realize is that before we begin to exploit our rivers, we must ensure that they have water flowing all the time in these rivers. And for that, it's the groundwater flows that have to be conserved or regenerated. And for that, spring shed and watershed management is absolutely essential. There's a Pune-based organization, best in the country, Aqua, and our own organization, People Science Institute, and several governments in the Northeast have done excellent work to promote community-based spring shed development. The beauty of this approach is that it does not take even a year to regenerate the spring flows. And this is another example of what have been traditional methods of doing the same. It requires integrated national natural resource management, which in this picture I'm showing is seen from a village in Garhwal, but it's also practiced throughout the Himalayan region, whether you go to Himachal in the west or you go to Arunachal in the east, you will find all kinds of water harvesting practices. But this has been possible only because of very high autonomy in resource management. We don't have that autonomy today. The shrinking flows need to be revived, and primarily it's the subsurface flows. And we must now begin to focus on minimizing the long and the short range threat to our glaciers. Wherever the dams are existing, we must ensure that they release at least environmental flows downstream of the dams. Just to give you an idea, the government of India has recently come out with some rules back in 2018, where for the Himalayan region of the Ganga, they had proposed, I think the maximum amount they had proposed was about 35% release of water downstream from the dams. But our calculations indicated that it should be at least 51%. We need to restore river water quality. We don't measure enough parameters. We are only looking at physico-chemical parameters. We don't look at the agricultural pollutants and some very basic industrial pollutants. And again, cannot emphasize enough how important it is to manage sediments. You know, it was absolutely stunning when I read an interview with the general manager of the Farakka barrage, who said, we had no idea that the rivers bring down so much sediments. This is a statement made after the barrage was built. And even a villager can tell you how much sediment comes. The impact of that is that the Farakka barrage today is almost useless, that there's huge amounts of sediments piled up behind it. The entire Ganga river has shifted several kilometers away from its banks in Patna and Bhagalpur, upstream of Farakka barrage. We need to protect the wilderness. We need to protect the upper reaches of these rivers. And we have done something towards that. In 2009, the National Ganga River Basin Authority decided that the stretch from Gaumukh to Uttarkashi would be maintained as an eco-sensitive zone. Similarly, in Himachal Pradesh, a small first-order stream, Tirthan River, has been declared as a wild river. But there are many more rivers that require eco-sensitive zones. And my own suggestion is that the upper reaches of all our Himalayan rivers should be eco-sensitive zones. They offer tremendous livelihood opportunities also in the form of local tourism. And finally, something that we simply forgot, the basic wisdom about water that was known to us. And I'm referring here to Rishi Kashyap. Rishi Kashyap wrote the Vishwavalabh, in which he defined 5 principles of water management, more river management. The first one is you build a temple at the source of a river. When I first read it, I was amazed. I thought, what on earth does a temple do? But then a friend of mine told me, he said, you know, a temple will have a pujari, a priest, and from that height, the priest can look and see that the river is not being abused. Second law that he recommended was that there should be minimum obstruction to the flow of a river. And so I call him India's first anti-dam protester. The third one is that forests and rivers have symbiotic relationship, and you should build water harvesting structures inside forests, like it's shown in this picture. The fourth is that we should not be polluting our river waters. And the fifth is that each one of us can contribute according to our capabilities to the maintenance of our flowing rivers. Thank you very much. I hope that you have enjoyed what I learned over the last 40 years. Thank you.
Thank you, Dr. Chopra. I think for that unique perspective, I don't think that any of us here had this whole idea about the Himalayan rivers and what is happening, and also the science of all of it, and also the traditional aspects that you added towards the end. Thank you so much. There's a lot of, in the chat box, I can see comments about your presentation. That was superb, excellent. There is Mr. Sanjay Gupta from the Alliance for Rivers in Indore, who has said it's a great presentation in your evergreen, most motivating voice. Indeed, sir, that your entire presentation has opened our eyes to a lot of things. I just had, I mean, you have practically given us the problems and also the solutions. I mean, but in terms of the larger perspective, I just had a question that you mentioned about these dams, that in Uttarakhand, there are so many small or large hydropower projects coming up. And I'm sure there are more planned probably. So is this trend going to continue? Is there something else that we could do? Can that be stopped? Can it be reversed? Can we have any other solution towards, you know, because you mentioned about the flow of rivers not interfere with the flow of rivers. And what we are doing with the dams is exactly that. So is there something that could be done? That was one question I had in mind.
Okay, we are very fortunate that in Uttarakhand, there has been a lot of concern and consciousness about the well-being of the rivers. The state government had a plan to build 450 projects in the state. But because of the protests, many of these projects are now being cancelled. The ones that are going to survive are going to have to. There is legislation on the cards to release environmental flows. Okay. But I think what we need to realize is that the era of hydropower is almost over. And that is because of economics. Today, it costs us somewhere between 6 to 8 rupees per unit to produce 1 unit of hydropower, electric power in a large project. And in a small project, it may go up to about 10 rupees per unit. Whereas solar power, which I can generate from the top of my roof, that I can bring it down to about 2.5, 3 rupees per unit. With those prices, I think you will see more and more shift to solar power. And I hope that architects like you will promote that.
Absolutely, absolutely. And I'm so, after seeing all those pictures of the Alaknanda, Bhagirathi, I just feel like taking my bags and traveling there right now. But one more question probably related to climate change. This is not in our hands because it's a global phenomena. There are lots of things that is beyond our control, and yet the glaciers are melting probably because of this. And all those things that you mentioned about the sediments, and we saw this dramatic picture of the landslide, etc. So, I mean, what can be done to halt or to do something about such disasters? Can we predict them, or help people not to be affected by this kind of disasters? What can be done in your view? One, about the glaciers melt, can anything be done at all? Because I know that you mentioned about plantations and management, etc. But about the glaciers is one big question. And secondly, about these disasters and the loss of lives, can something be done?
As far as the glaciers are concerned, a lot can be done. First, it's important to realize that forests are the backbone of the mountain environment. Forests have to be absolutely protected. And we have to be very careful when we are designing projects like roads in the Himalayan region. Very recently, the Supreme Court committee that I'm heading at present, we've done a calculation to show that there is a tremendous amount of carbon dioxide that is being generated because of the summer traffic of tourists going up to Badrinath. And the government of the state, because it is cash strapped, it believes it is cash strapped, wants to push 10 times more tourists into that valley. Now, that again is a paraglacial valley. And with all that building construction that will take place, the whole place is going to become warm, and it is just surrounded by glaciers. Okay, we've got to become much more environmentally conscious. We have helicopters flying up to Kedarnath, and helicopters run on fossil fuels. Okay, they generate a lot of particulate matter when they are up in the sky that falls and leaves behind patches of black carbon soot, which can be measured now. It's not distributed that much. So these are some of the things that we have to be extremely careful about. And as I said, even the enormous amount of pollutants being generated in the Indo-Gangetic Plain finally ends up over here. Okay? So we need to move away from fossil fuels. That is for sure. Okay. As far as motor vehicular traffic is concerned, we've got to protect our forests. We just have no choice in that matter. Now, as far as predicting disasters go, there is a little bit, there's growing knowledge, I would say, but still it is quite limited. We've had a wonderful meteorologist in Dehradun. 4 days before the 2013 disaster, he informed the state authorities that we are going to experience unusual downpour. There was only one police officer who responded to him and tried to evacuate that valley. But The rest of the government just ignored. They thought, hey, this fellow releases these kinds of warnings every other day. So they just ignored it. We've got to take these things much more seriously. There are court orders saying that you cannot build structures on the banks of the river. Okay, you have to be at least 100 meters away, or some courts have ordered 200 meters away. Nobody adheres to that. The government simply ignores it. Okay, these are very basic things that we need to be careful about. There's this great fascination nowadays. If you look at the British roads, they are up on heights, far away from the river. The modern tendencies, everybody thinks about, let's have a marine drive by the side of the river. Okay. Now, when you build that road, what do you think is going to happen? Commerce is going to come right there. Hotels, restaurants, all kinds of establishments will come right by the riverbed. And what is the road built on? It is built on mud that is brought from somewhere. So it is very weak. And the rivers can easily, a good flood can easily wash away that base. Okay. So there's quite a bit we can do.
Thank you. There is a question from a student, first year MTech student, Shruti. She says that, can you throw some light on research area or topics that can be taken by MTech students?
It depends what your interest is. I'm quite fascinated with working on how much environmental flows do we need at any particular point in a river. There are different approaches to that, but what has been fascinating me is that in India, we tend to worship rivers, right? And so far, what we found that in the Western literature, there is no consideration of social, cultural, and spiritual water requirements. Now, that's a very important area of research, at least for rivers in traditional societies. And you will probably remember that the judgment in New Zealand about a couple of years ago, where a river was declared as a living entity. If it's a living entity, how much water does it need for its life?
Great. I think that's a good area of research for you, Shruti. There's also one more question. The name is not clear, but sir, any research on the South Indian rivers and dams? Is it available?
Oh yeah, there's a fair amount of research and good research. In fact, I admire the work that is being done in places like IEAR or the Indian Institute of Science in Bangalore many years ago. There are a lot of problems on the rivers that flow west into the Arabian Sea from the Western Ghats and the Nilgiris, as well as a lot of work done on the major rivers of South India, the Godavari, the Krishna, the Kaveri. And for example, International Water Management Institute has shown that Krishna is now a closed river. There is no water, there's not enough water or sediments flowing into the delta.
Great. I think we don't have time, but I just would like to summarize what Dr. Chopra has enlightened us with, and he has said there's a lot we can do, and that's very important. We have to be more sensitive towards the way we construct, the way we deal with our natural environment. We have to do a lot more about the forests. And if he says that the glaciers can be protected, a lot can be done about the reversal by improving on the forest ecosystems. That is a big lesson for us to begin with, at least. And overall, he said about fossil fuels, that we have to move away from fossil fuels. So thank you so much, Dr. Chopra, for being here today, for enlightening us. And I'm sure there are lots of questions here, but I will hand over to now Sneha for the next speaker.
Thank you very much.
Thank you.
Thank you, Roshni ma'am. Thank you, Dr. Chopra. It was indeed mesmerizing. I welcome our next speaker, who has joined us from Israel, Mr. Avraham Israeli. Mr. Avraham is an economic and environmental consultant, MOAF, and past president, Israel Water Association. His areas of specialization include professional water, agriculture, and environment consultancy with strong managerial and business development expertise. He holds an MSc in Agricultural Economics and a BSc in Agriculture and Economics from Hebrew University, Rehovot. He has held many designations over years, including Executive, Israel Export and International Cooperation Institute, Managing Director, GAD Semiconductors, Migdal Hamek, Marketing Director, Yana Plus Limited, Ramla, Secretary General, Kibbutz Nakshot, Kibbutz Federation, New York, USA, Head of the Department of New and Small Kibbutz Communities, Kibbutz Federation, Economic Director of Kibbutz Nakshon. He has over 27 years of experience working with foreign and Israeli companies, government organizations, and is involved in water projects worldwide. I warmly welcome Mr. Avraham Israeli. Over to you, sir.
Good morning, everybody. Good afternoon to you. I would like to share the screen. Well, my name is Avraham Israeli, and I come from a very little country, Israel. After hearing all the problems of great India, our problems are very, I must be very humble when I'm speaking about the experience of Israel, but I think that Israel underwent some experience that can be shared, and we are very happy to share it with you. Well, this is the map of Israel. Israel is, like I said, very small country, only about 21,000 square kilometers, but it is very diverse from the climate point of view. In the north, above the red line, there is rain that changes between 500 and 900 millimeters per year. And in the south, it goes down to 25 millimeters per year or even less, which means a total desert. And Israel had some challenges how to bring water from the north to the south. This was the first challenge of water that Israel faced after its foundation in 48. Now, Israel built a national water aqueduct from the Sea of Galilee. You see it in the north of the country, here, down to the south to bring water to the thirsty area of the south of Israel. You see, not all the southern part got water from this. It was not enough. However, it enabled the southern parts of the country to conduct agriculture, and it was bringing enough drinking water to the population. You have to take into account that the population in Israel, when it was in 48, it was about 1 million people altogether. Jews and Arabs, it became today about 10 million. So the growth of the population was such that needed a lot of water to be added to the all water package. Now, so there was a very big gap between and the gap was growing between the supply and demand of water. And Israel had to close this gap. And how was it done? First of all, there were steps to reduce water demand by water saving education and water saving campaign that explained to the people how severe was the situation and encouraged them to save water by education and by all kinds of devices, the domestic devices to save water, but it was not enough. And therefore, the irrigation, which you'll see later, agriculture is the #1 consumer of water, not only in Israel, I believe it's all around the world, but Israel developed advanced irrigation that enabled to keep the yield or even increased the yield of the crops with a saving of about 30% water. And that was one of the achievements. You will see it later on also. There was better water management. Before that, every step in water, every project or whatever had to be dealt in about 5 or 6 ministries, the Ministry of Internal Affairs, the Minister of Environment, the Minister of Infrastructure, etc., the Minister of Health, and then the Israel constructed the water authority that was in charge of all the aspects of water development. Another step was prevention of leakage and losses from the system. This is one problem that, as far as I know, affected many countries, and Israel was included. And there were some technologies to detect and correct losses in the system, leakage and losses in the system, and that now the losses are minimized to about 10%, not more than that. And the economic measures that were taken were to increase the consumption tariffs. And this was maybe one of the major issues, because if there is no charge for water use, or if it's a constant or like tax that is charged to the people, people don't mind to waste water. But if they pay according, even small amount of money, if they pay according to the use, people intend to save more water. And that was something that was very important, to put water meters in every consumer and to pay according to the use of the water and not a constant amount. But on the other hand, Israel had to increase the water supply. And the use of wastewater, mainly in agriculture, was one of the main measures. And then it came to desalination. This was the last step, because desalinated water is more expensive, but there was no chance. Israel had to start desalination of brackish and seawater, and you'll see how it was done. Okay, I want to summarize how to closing the gap was water saving and efficient use of water, water tariffs, water wells purification, because many of the wells were polluted and it needed a very special technology to purify wells and the aquifers, and it brought water quality improvement, increasing capacity of wastewater treatment and upgrading the affluent quality. And then the last measure was desalination. Here you can see in this slide, on the right-hand side, you can see what the campaign to save water, every drop counts. And on the left-hand side, you can see the irrigation with drip irrigation, which I'll talk a little later. Water tariffs, as I said, were the basis for a sustainable water infrastructure. Even the urban and industrial tariffs, as well as agriculture water tariffs. And these are the tariffs that were paid by urban industry and agriculture. You see, it's not very cheap, but it was affordable, and people agreed to pay according to the use. Now, the increasing capacity of wastewater treatment was a basis for increasing the amount of water that was available for agriculture. I must say that without the reuse of water, Israel would not be able to have any agriculture, or almost any agriculture. And you'll see later that most of the water that goes to agriculture is treated wastewater. But in order to do it, Israel had to develop an efficient way to upgrade the level of wastewater up to tertiary treatment that enabled unlimited irrigation. Before that, when most of the wastewater treatment plants treated only to the secondary level of treatment, only non-food crops like cotton and hay and some other crops could be grown with this water. But there was a new law that all the wastewater treatment plants should upgrade their treatment up to the tertiary treatment level, so it enables unlimited irrigation. And there was more construction of new water reuse systems, and there was a problem to encourage the farmers to use effluent instead of fresh water. And I can say from my own experience, when the first time that the authority came to us, when I was still a farmer on the kibbutz, and tried to convince us to use effluent instead of fresh water, we didn't want. We didn't know what will be the effect of using wastewater treatment, wastewater in agriculture. And then they had to convince us by giving us a larger quota of water, because each farmer in Israel had a quota of water that he could use, not more than that. And we got larger quota if we agreed to use effluent instead of fresh water. And then we agreed, and we learned that we are not losing the crop, but vice versa. Because of the nutrients that were in the effluent, nitrogen and phosphorus, we were able to increase the yield with the effluent when we used it. And this way, the farmers were convinced to use the effluent instead of fresh water. Here you can see the largest wastewater treatment plant in Israel, which is near the city of Tel Aviv, and it serves about 2 million people in the Tel Aviv area, and it treats the water up to the to tertiary level, and all of this water goes to the southern part of Israel to be used in agriculture. But when I said that the population increased and the standard of living increased, people needed more water. So there was no alternative to start to desalinate. And the first desalination were all the brackish water that exist in some areas in the south, in the desert. There was groundwater that were brackish and couldn't be used like as is. So some technologies were developed to start to desalinate brackish water, and the improvement brought the cost of brackish water desalination down to be affordable. And then the last measure, or the last step, was to start to desalinate seawater from the Mediterranean. As you saw on the map, and you'll see it again in a minute, Israel is located by the Mediterranean Sea, and therefore there's no lack of water. There is a lack of fresh water, but Israel has enough seawater to be desalinated. The only problem was technology and cost. And this is, again, the map of Israel, and you see the Mediterranean Sea all along Israel, and therefore the desalination plants were developed in the last 20 years, and now there are this list of plants that you can see. Most of them are already operating. Some of them are under construction or under the design. And this gives enough water to Israel. And but of course, there still is the issue of the cost of desalinated water. And this is the total cost when you see at the bottom of this table, and the last one has the lowest cost for desalinated water. It is the largest one. It is one of the largest reverse osmosis desalination plants in the world. which brought the cost down to about $0.50 for a cubic meter. And this was just quite a revolutionary cost, because before the construction of these plants, the cost was around and above $1 per cubic meter, and this brought the cost down. But it was done because the main ingredient of the cost of desalination is the energy. And the energy was reduced from about 5 or 6 kilowatt hour per cubic meter to less than 3, in sometimes 2.5 kilowatt hour per cubic meter. And to deal with the environmental issues, each desalination plant, the big ones, constructed independent power plant that was powered by natural gas and not by coal, and this way reduced the potential pollution of the air. And another environmental issue is what to do with the concentrate, because when you desalinate seawater, 50% of the water in the intake goes to become fresh, and 50% become the concentrate that has to be discharged. And so we're developing advanced diffusers to discharge the concentrate back to the sea without making any environmental harm to the sea, to the fauna and the flora of the sea. And the second measure was to monitor the discharge, and in each place where the water is discharged, there are monitoring stations to see that there is no pollution in the sea. And what I said is to use natural gas, and hopefully even natural gas will go down when the solar energy sources will be more and more in use. Now I would like to share with you some water technologies that were developed in Israel. And first of all, in agriculture. As I mentioned before, the drip irrigation was developed here in Israel. And as a matter of fact, I had the chance to be one of the first users of drip irrigation, which at the beginning was not so efficient, but gradually was developed more and more to avoid clogging in the drippers and to make the drippers longer, drip lines longer and more efficient. And what are the advantages of drip irrigation? The drip irrigation, it can save up to 50% of the water while increasing the yields by 30% in many, many crops. And this system was adopted largely in many, many countries, especially where there is a shortage of water, but not only, because it is efficient even in places that water is plenty, but you can increase the yield of the crops, and this is a main advantage. How does it work? Here in this slide, you can see a tree and the drippers, the drip irrigation, it is around the root environment, the root space, and not more than that. By that, you use all the water efficiently for the crop on one hand, and on the other hand, you avoid the water to penetrate to the ground water. And this is one of the main issues that enable drip irrigation to be the best method for irrigation with wastewater, treated wastewater. Because even in treated wastewater, you want to avoid or to prevent this water to mix with the groundwater, the fresh water that goes for drinking, and drip irrigation is the best way for that. And it can be easily and optimally combined with fertilization, and it is called in English a new word, fertigation. That is the combination of fertilization and irrigation. And the advantage is to bring exact amount of fertilizer to the plant without the possible penetration to the groundwater, again, like the wastewater. This is one thing. Another advantage is that you can change and optimize the intervals between the watering cycles. It can be once in 2 days, in 1 day, even you can make pulse irrigation for very sensitive crops that can be optimized and increase the yield. And of course, there is no sensitivity to winds, like in the spraying of water in sprinklers or other ways of irrigation. Like I said, it is the optimal method to use reclaimed water. It is not sprayed, no drift, no droplets, and it is not sensitive to winds. It is watering only to the root environment, no infiltration to the groundwater, and there's a minimum possible touch between the upper parts of the plant and the water. And it enables another way of irrigation, which is the subsoil drip irrigation, which I'll show a little later. Here you can see some drippers, all kinds of drippers. Some are within the line, some are implanted outside of the line, but these are the drippers, and here you can see a drip line before it is installed. Here is a way how to install the drip irrigation in a field. You can see here that the water comes from the well, it being filtered, and then it goes to the main line, and from the main line, it goes to the drip lines, and this is how it works. Very easy to install, and it is very efficient. Now, like I said, and Roshni, will you be able to upload the short video, if it's possible? And I would like to show you a two-minute video how the subsoil drip irrigation works. It's coming. You can see here the crop, and you don't see any lines of irrigation. And the surface of the soil is dry. It is another advantage to avoid weeds on the field. Here you can see the subsoil drip lines and the cultivation of the ground without any interference. Okay. Okay, back to the presentation. Okay, like I said, Israel recycles most of the wastewater. It's in this diagram, it's about 80%, but it's close to 90% nowadays. Of the wastewater in Israel is treated and reused in agriculture and in some cases in the industry. Now, this is a diagram that shows you the allocation of water. And you see in the blue part, the domestic use is less than 50% of the water, available water. And it is very similar to the amount of water that is desalinated. So practically, it means that the potable water in use is almost all comes from desalination. And on the right-hand side, in the green line, you see more than 50% goes to agriculture. But if you see on the rectangle on the right, that more than 50% of the water in agriculture is recycled water. And only less than 50% is fresh water, potable water, that goes mainly to sensitive crops like avocado, mango, and some other crops that are very sensitive to salts and other impurities of water. Just one more issue that I want to mention, that the desalination improves even the wastewater qualities, because when you treat wastewater, you don't desalinate it. And then, therefore, because of the use of salts, the wastewater, even the treated wastewater, has much more salts than it was before. And it is, for the long run, it is not good for agriculture because of the salts. You get more sodium and chlorine, and it is not good. So by using desalinated water in the wastewater treatment plants, you reduce the amount of salts that are in the treated wastewater, and this way, you in the long run, you get less salts in the ground, in the soil. Now I'm coming to some samples of technologies that were developed in Israel. And this one is a technology that increases the capacity of wastewater treatment plant by a very special technology. It introduced very little particles of plastic to the wastewater treatment reactors, and by that, the colonies of bacteria that actually are cleaning and decomposing the organic matter can grow much more and upgrade the process of the treatment. You see there is a cycle, and these are the particles. On the right-hand side, you can see very small particles, very specially shaped to give the colonies of bacteria the best conditions to grow on. And this way, they can increase the capacity of the existing wastewater treatment plant. This is how it is built. It is very easily to come to an existing wastewater plant and to increase the capacity. And these are the benefits of this process. No additional area is required to build a new basins. Upgrade time is much shorter. No permits are required because it's on the same area, and the expansion can be gradual, allowing to spread the upgrade expenses. And the effluent is excellent quality, and there is intensive nitrogen removal, and it is very efficient. Here you can see one of the implementation, and you can see the white particles within the water reactor. This is another technology that comes to an extensive existing pond for wastewater and upgrade it by a very simple floating aerator, because I hope that you know that the aerobic part of the process of wastewater treatment plant is very essential, and it needs a lot of energy. And this way, by introducing floating aerators to an existing pond, like in this example, it is very easily done. in 1 day or 2 days, you can introduce, you can construct all the needed aerators, and it improves the quality of the wastewater very easily. Here you can see a very small, on the right-hand side, you can see a very compact process for domestic wastewater treatment plant. It is based on a few tanks under the ground, where it is aerator. There is an aerator, very small one, that brings oxygen to the water, and it is done very easily, and you see nothing, and you get good enough water to irrigate a garden, whatever. In the left-hand side, you can see the biodisk technology, which enables treatment of large quantities of water. It is modular. You can bring another biodisk unit if you need to upgrade it. So it is very flexible to the quantities, and the results are very good. Here you can see the explanation, what are these two technologies. Now I'm coming to the technology that is imitate a natural wetland. It is called the constructed wetland, and or wet park, and it is artificial wetland, and it is created for anthropogenic discharge, such as wastewater, stormwater, runoff, sewage treatment. And it is like natural wetlands. It acts like a biofilter, and it is able to remove sediments and pollutants, even heavy metals, from the water. And this is how it is constructed. You see, this is the beginning, the first stage of construction. The water flows under the surface. You don't see the water. You put it in one side, and you get the effluent from the other side, and the plants that are planted purify with their roots. They purify the water. And here you can see how the same place is seen after 2 years of the construction. You see just green plants. You don't see the water under the surface, but you get cleaner water. If it is well planned, well designed, the water is treated very well by these plants. And these are the advantages. It is, if it's properly designed, you don't need a lot of energy, almost no energy at all. There is no odor because the water flows under the surface. The landscape is very nice, and the treatment results are very good, and this is the most important issue. But there are disadvantages, of course. It is good for single house or for single farm, small community, and it needs wide area. Sometimes it's not available, and it is not appropriate for a large community or city or whatever. It is good also to rehabilitate rivers, and it brings down the BOD, the COD, and all the other pollutants. And these are the reed plants that are planted there in order to do the job. Here you can see some examples in a river in Israel, where some plants, these reed plants were planted, and they rehabilitate and clean and treat the water, and the water later on is clear and clean. Here you can see how it treats some small petrol gas station sewage, and it treats it very well. Now I'm coming to the disinfection of treated water, because you know that if you treat water to a tertiary level, you have to disinfect the water from bacteria, pathogens, and this has some possibilities. One of them is to add chlorine to the water. Another is the use of ozone to disinfect the water. But another measure is to treat it with ultraviolet technology. And this can be very efficient and even cheaper. And this is an example of ultraviolet device that you can put water in one side and get disinfected water on the other side. Within this device, there is a radiation of ultraviolet that kills all the pathogens. Here how it works, another device. And just I wanted to mention that there is another startup in Israel that uses LED instead of the regular UV lamps, and it is called UV LED, and this way it makes it use much less energy than the regular UV lamps. This is the chart of the desalination in the world. You see how quickly it grows because of climate change and the water availability of water in many, many areas in the world. This is the first desalination large plant in Israel in the city of Ashkelon that was constructed, and it treats about 100 million cubic meters a year. And it was the first one of a series of 8 other desalination plants. And you see that it has its own independent power plant that supplies clean energy to the plant. This is another device to separate particles from water without a filter, and it is called Aqua HD separation unit, and it works with centrifugal power, and there is no moving parts. Only the water goes in these tunnels. You see on the left-hand side, it's a diagram. In the right-hand side, you see the device itself, and it separates the particles from the water. And you see here, they took water from a lake that was infected by algae. And after using this device, you can see on the right-hand side, the treated water, and on the left-hand side, you see the water like it was taken from the lake. Here you can see water full of mud from a pack house of sweet potatoes in this case. And after using this device, the water can be recycled back to the same process and no fresh water, more fresh water is needed. Now, the last part of this presentation, I want to mention some cooperation between India and Israel to prepare a water master plan in some regions in Israel. The first one is in Maharashtra, India, not in Mumbai, but in Marathwada. I hope I pronounce it well. And an Israeli water expert is completing his 3 years working in India with the regional authorities of this region to prepare a master plan, because a master plan is the basis for improving the water situation in the region or in the country. And this is another place in another regional master plan planning in Punjab, in the northern part of India. And hopefully this master plan that was designed will improve the situation and improve the relations between Israel and India generally. And this is the end of my presentation. Thank you very much. I am very honored to be part of this great event.
Thank you, Mr. Abraham Israeli, for taking us through Israel and all the technologies, especially that has been invented. And I think 3 things come out as an outcome of your talk. One is about the water tariffs, how to value water, which is one of the reasons. Like in India, if you do a water recycling project, you are not able to show any paybacks, because the cost of water here is very low. So water tariffs, of course, is an important aspect that you mentioned. The second aspect, I think, is the treated wastewater. It's amazing that Israel is almost treating 90%. That's, I think, the highest in any part in the world, and using it for agriculture. And the third thing is all the technologies that are being used in desalination and also in other wastewater treatment. So thank you for taking us through that. And there are lots and lots of questions here. I'm not sure if I can ask all of them, but few of the questions are related to desalination. So I'll sort of club them together. There is one Dr. Manjunath from first year student of VTU, of Water and Land Management VTU, who has asked about economical methods for seawater desalination, because I think the concern here is that desalination is not economical, especially in India. Then I think there's one question by Sujnani, which is also related to desalination, but I think we can discuss that. She has asked another question here. So I think we'll first look at desalination, and there are some more questions on drip irrigation.
Okay. Of course, desalination is more expensive than using natural water. If you have enough natural water, you don't have to desalinate. Maybe in some regions, but not generally. But in places like Israel, where Israel is a semi-arid place, region, without enough water, you need to increase the amount of water. And desalination is, like I said, was the last step of bringing more water to be used. Now, the challenge is how to reduce the cost of the desalination. It was done by reducing the need of energy for the desalination. And it was done by recycling the energy Within the process, the energy was mainly needed to increase the pressure. I didn't enter to the technology itself of reverse osmosis, but mainly it is when you bring water to a very high pressure and you push it to membranes, within membranes that enable the molecule of the water to pass and the molecule of the salts not to pass, then you get clean water on the other side of the membrane. But it needs a lot of energy to raise the pressure of the water up to 70 bars, 70 atmospheres. And the technology was how to use this high pressure water and not waste it after the water goes through the membrane. And this was one of the inventions that was done in these plants in Israel that enable to recycle more than half of the energy that was invested into the process. And this was what enabled to reduce the cost of the desalinated water from $1 to about 50% of that. Now, there are other ways of desalination, thermal desalination or distillation, it is called, but it needs a lot of energy or residual heat that can be used for that. And Israel doesn't have this kind of energy, so reverse osmosis was the most effective way for desalination. I hope that
yes.
answered.
Thank you. Thank you. Yes, that more than answers the question. Mr. Sanjay Gupta here says that we need a center in every district across the nation to teach these techniques and methods. He means all the technologies that you talked about. There is a question from Anjali Butner. She's asking you how much percentage of agricultural land is covered by drip irrigation in Israel, and how much is it per hectare?
How much is it? How much does it cost for hectare?
Not clear, but maybe I think Anjali.
I don't have the figures. How much does it cost? It changes. But I can tell you that it pays back very quickly. Even if it needs an investment to introduce the drip lines and all the system, to the filters and all this, like I showed in the presentation, but it pays back in 3-4 years. You get, you use less water, you get higher yields, and you pay back the investment. How much water, what is the percentage of the drip irrigation? I think most of the irrigated area in Israel uses drip irrigation. I don't have the number. There is, in some places, there are sprinklers still, and moving line, another way of irrigation, but most of the fields are with drip irrigation in that. And I can tell that in many places in the world, drip irrigation is getting more and more popularity, and in spite of the investment that it needs, the advantages are so big that it is introduced more and more.
Thank you. Sujnani has a question, and also Akshata Bandi has a question on drip irrigation, so I'll combine them. Sujnani is asking about drip irrigation in hilly areas. She feels that this is a problem, Can you tell us about it? Can you tell us how to deal with it? And then Akshata asks about opportunities in advanced irrigation, which can be taken up as research work.
Well, in the Hilly area, drip irrigation is possible because now all the drippers are regulated drippers. It is flexible to the pressure that gets in, because in the hilly place, the problem is that in some places the pressure of the water will be higher than the others. But because of the fact that the drippers are regulated and they emit exact amount of water per minute, even if the pressure is higher or lower, the hilly places are very good to be used in drip irrigation. And there's no problem, if it is well designed, it is no problem to introduce drip irrigation in hilly places. What was the second
was
question?
about areas of advanced irrigation, research areas that could be taken up in, this is a student who's asking about advanced areas in irrigation, advanced irrigation, opportunities in advanced irrigation can be taken up as research work. Is there something that you could suggest based on innovations that Israel has done?
Well, of course, the issue is how to reduce the cost of irrigation and to improve the quality of the drippers. And as far as I know, some of the Israeli drip irrigation companies are cooperating with the Indian companies. One of them is a Jain company, which is a partner of an Israeli company. Another one is, there is another company in Israel that has a partner in India. And I'm sure that there are a lot of areas to be studied and to make a research in order to improve and make it more efficient.
Yes, I think it's Nandan Jain and also Neta.
Yeah, Nandan, yeah, exactly. Jain is the Indian partner. Nandan is the Israeli partner. And I live very close to their headquarters, so I know them very well.
That's right. There are a few more questions on drip irrigation and also wetland management and treatment. So Professor Rohan asks here about important effective shrubs that can be used for wetland management and treatment. And the same question is asked by Anand as well. And the second question by Anand is about underground drip irrigation. What are the challenges as, is there like a penetration of roots into the pipes? Does it happen?
Yeah, it was, I don't know if they paid attention to the video. He dealt with it, and there is a problem of penetration of roots or plants into the drippers, but it is avoided by special material that is giving to the drippers, and it emits very little microscopic droplets of this material that avoids penetration of roots. And as a matter of fact, this was the main obstacle to use subsoil drippers, but now it is solved, and it works for many years without any penetration of roots. And it enables not to collect, because, you know, when I was a farmer and I grew cotton and we used drip irrigation, we had to collect the drip lines every year in order to let us cultivate the land. And then in the next season to implement the drippers again. Now, if you have subsoil drippers or drip lines, you don't have to collect it. It stays in the ground for years, and it is very efficient and very comfortable for the farmers. What was the other question? I forgot.
It was about plants for wetland management. What are some of the plants that you would...
These are mainly if you are talking about the constructed wetland. Yeah, there are many kinds of reed plants that are used that have the ability to treat and clean the pollutant, the nitrogen, the phosphorus, and the heavy metals from the water.
Yes.
Okay.
Yes, thanks. I think just would like to add that in India, the plants like banana, the what do you call aloo plant, and a lot of ipomoeas, even bamboos are used for wastewater in these wetland systems.
Bamboo, I know. I don't know about using banana trees for that, but I don't have the experience with banana trees. I like banana trees, but not for treating the water, but maybe, I don't know. But
in traditional houses in the villages of India, we know that the wastewater is often left out, and it is left out to a bunch of banana trees, and that's the traditional way it is done. So I'm just saying from that experience.
I learned a new thing now.
Yes.
Thank you, Roshni.
Thank you, Mr. Abraham Israeli, for taking all the questions. I will pass on if there are more, since we are closing the time. There was one question from Dr. Archana Bhatnagar for Dr. Ravi Chopra, and this was on a river linkage project. What is the feasibility and outcome?
What again?
Sorry,
there is a plane outside.
Okay.
Making some noise. Sorry.
Okay. No, so this question is for Dr. Ravi Chopra, was asked from his first presentation for Dr. Ravi Chopra.
No, I can't get the question.
Okay.
There's too much noise here. Sorry for that.
No problem. It's a question addressed to...
I would be more than happy to have questions. If they can send me the question, you can pass them to me, and I'll be very glad to answer every question. And even I didn't speak about my present activity, that I'm now involved in a project in Latin America. But the last two slides that I put about the cooperation with India was done by one of my current team that are planning similar master plans in Latin America, like we did with India. And it is very challenging to deal with this kind of water problems in all kinds of developing countries. And I hope that we'll be able to share the Israeli experience in India, in other developing countries. And I'm very humbled to say that.
Thank you, Abraham. Thank you so much. Thank you.
Thank you for having me.
Yeah. Dr. Ravi Chopra, there's a question regarding the river linkage project, the feasibility and outcome. So maybe you can enlighten us. Thank you.
Yeah. The whole idea of interlinking rivers is based on a very myopic understanding and view of rivers. This is again an engineering view where you are simply looking at how much water there is in the river and how much is being used today. If you look at it first of all, the basic concept that there are some surplus basins and there are some deficit basins is incorrect. There is no surplus basin. Today, I think today the Prime Minister is going to announce some start of some interlinking project, the Ken-Betwa River. Many years ago, we had done a comprehensive study of this project. And what we had seen was that Ken River is does have water flowing in it all the time, primarily because there is no industrialization in that basin to speak of. There is very little cultivation. Much of that region is a forested region, and therefore it's a largely tribal region, and there isn't much irrigated agriculture. Now, if tomorrow the people of the Ken Basin decide we want the same kind of development that is there in the Betwa Basin, then where is the surplus? Okay, so then it becomes a political problem. Secondly, if we are only going to look at water and we don't recognize the river as an ecosystem, then how much we will convert the entire river, we have no idea about. The kind of organisms that need water, how much water do they need, and how the whole food chain of the organisms is built up. Engineers have no idea. In fact, I should have said in the first round that it's extremely critical, to my way of thinking, that there should be basic courses on ecology for all students. Just like we have maths, physics, chemistry, etc. for the engineering, architecture students, we need ecology as a basic subject. We must begin to understand ecosystem. So if you look at it from that point of view, these are really silly ideas. Okay? And I would urge that student to actually take up a river linking project and study it, and then develop her own understanding and views. I'm quite sure that she will not be disagreeing with me at the end.
Thank you, sir. I think that question was asked by Dr. Archana Bhatnagar from SNDT University in Mumbai, and she would probably guide a lot of her students in the direction that you have given. And there are a lot of engineering students as well who might get the right answers from the answers that you have given. So now I think we are already running a bit late, and over to you, Sneha.
Thank you, Roshni ma'am. Thank you, Mr. Abraham, and thanks, Dr. Ravi Chopra. We'll be breaking for lunch for 45 minutes and continue our interesting session post-lunch. Hello, and welcome back to our post-lunch session of the International Symposium on Valuing Our Water Resources. To brief you all, we had Dr. Ravi Chopra and Mr. Abraham Israeli as our speakers with an interesting discussion before lunch. Now we continue with our webinar with our next speaker of the day, architect Nandan Mungekar from Mumbai. Mr. Mungekar is an architect, interior designer, engineer, town planner, environmentalist, a government-approved valuer, and an expert in dowsing and pendulum diagnosis. He holds a government diploma and a bachelor's degree in architecture, an ME Civil in town and country planning, PG diploma in environment and ecology, certificate course in geology, and is presently doing research for doctorate in environment and ecology. Architect Mungekar is proprietor of Mungekar and Associates, Mumbai, and has completed more than 1,000 projects successfully related to rainwater harvesting. He is currently designing rainwater harvesting for Shivaji Park at Dadar for mitigation dust problem, which is causing health issues in the neighborhood. He is a recipient of the Award for Excellence in Architecture 1998 for the project Roof Water Management of Holiday Home Training Center at village Bose, Panchgani. Award for Successful Rainwater Harvesting at Oval Maidan, Mumbai, and M.N. Banaji Industrial Home for the Blind. He has authored a book on environment studies titled use, misuse, and abuse of hills and its impact on city development. A case study in and around Mumbai. He has more than 40 years of professional experience and has traveled to more than 15 countries for professional assignments. I would like to welcome architect Nandan Mungekar. Over to you, sir.
Yeah. Good afternoon to my friends from India, and good morning to Mr. Abraham Israeli and Anjali Butler from Germany.
Thank you.
I'm really thankful to Indian Institute of Environmental Architecture and Research, Dr. Roshni Udyawar, and from Dr. Dr. Anand Shivapur from Visvesvaraya Technology University. Yes, the subject given to me is rainwater harvesting in the urban context. Yes, if I have to start for that, I must tell you the history about rainwater harvesting. People are aware with Ramayana, Mahabharata. In the original text of Ramayana, which took place 7,000 years ago, when Rama was sent to Dandakaranya is a forest with devoted trees. And why devoted? Because there was no water. And there, Sati Sita had to cook food for Rama. So she was not getting water. How to solve this problem? So this problem was solved by Rishi Atri's wife, Sati Anusaya, in the Dandakaranya. So the history of rainwater harvesting is 7,000 years old. Then comes Mahabharata. Lenardi is one of the temple carved in a hill, supposed to have been carved by Pandavas. I'll be showing some slides of that. It's a 5,000-year-old example of rainwater harvesting. Okay, come Pratapgarh. All the forts of Raja Shivaji, about 300 to 350 years ago, constructed. Every fort is having rainwater harvesting. That's how they could survive on the hilltops. When Abdul Khan had surrounded Pratapgarh, Shivaji Maharaj was sitting pretty for 1.5 years on the top of the hill, that is top of the fort. Then comes our Rashtrapita Mahatma Gandhi, in the place where he's born at Porbandar. In his house, rainwater harvesting is there. And in Gujarat, the tanks constructed underground where the water was stored, rainwater was stored, was called as a tak, Mahatma Gandhi tak. So that is Mahatma Gandhi's residence. And then comes the Rashtrapati Bhavan. Rashtrapati Bhavan is also having rainwater harvesting. So the history of rainwater harvesting starts from 7,000 years ago to up to now. So it's a old technology. Only we have forgotten this because we are getting water by taps in our houses. So we have forgotten this technology, which is a old and time-tested and very much required technology. Okay, now I will start with my presentation. Yes, rainwater harvesting. Now there are two basic elements. One is rooftop harvesting or roof water harvesting, and second is groundwater recharging. Roof water harvesting is fairly simple, collecting the roof water or water from impermeable area, filtering it and storing it into the rainwater harvesting tank. Rainwater from this for first 7 days is not collected. It is allowed to wash out the roof, which is called as the first flush. Then after that, the water is collected, filtered and stored in an impermeable area or a tank and used again. That's part of roof water harvesting. And ground recharging, the second most important, because roof water harvesting serves for 4 months or during monsoon. And after monsoon, for all the 12 months, collecting the rainwater, falling on the plot of land, percolating it into the ground at the hydrogeologically suitable points, suitable points, and thus increasing the groundwater table and using it for all the uses all throughout the year. History. This was the example which I was quoting some time back. This is Lenardi Temple. And here it is supposed to have been carved by Pandavas, where the roof water is collected or the water falling on the hill is collected. You can see us on the left hand side photographs, a small well from where the water goes inside a carved tank, and this same water was used for is used for all the puja and all process of Ganpati. So this is the oldest example in rainwater harvesting, Lenardi Temple. The second oldest example is available in Mumbai itself. These are Canary Caves. You can imagine this as your flat, and the top is terrace. You can see some scars on the top. These are the trenches. They are carved to take the rainwater down below the small cave. The people at that time also knew what is the rainwater like, 24,000 millimeter, exactly of that height. The tanks were carved out and all the water was taken into the tanks below the cave, and that was used all throughout the years. And while this water was coming from the top of the hill, it was being filtered in a different ways. Filtered from charcoal, filtered from alum, filtered through sand, and the purest form of water was being taken to the cavern below. These are the various ways, these are the various filters, and these are 3,000 years old. So this is working even till today. This is the second example of Janjira Fort. This is located inside inside a sea, surrounded by water from all the sides. But you can see water falling on the inside is taken in two ways. One, it is water which is falling on the land is collected into the two lakes or two ponds there, and the water which is falling on the turrets was taken into the well-like portion on the sides where the cannons were kept, and the firemen used to jump into that water storage tank when he used to blast the cannon. So this is the second example, and this is also from the time of Raja Shivaji. I had a chance of designing rainwater harvesting building with rainwater harvesting in 1995. That was a building which I constructed for Ion Exchange India Limited, and it was at Bhose, opposite Pratapgarh. When I was faced the challenge of designing this building, I was trying to find out whether there is any such building is there. And actually, at Panjgani Moral Rearmament Center, which is one of the building where they have collected water from the roof. You can see in the left-hand side picture that the downtake pipe is taking the water and taking it into the tank. There is a cover here which first 7 days water was not taken in, which is allowed to clean the roof. And after cleaning the roof, this cover was removed and then the water was taken into the tank. This simple method being practiced there for last 70 years. These traditional methods are based on scientific principles. These methods have been understood, modified, and adopted to the modern day requirements today in all my designs. Rainwater harvesting in modern day architecture. It is a time for us to realize that the rainwater harvesting is not just meeting the water requirements, but it is also to be made an integral part of our building design. Incorporating the rainwater harvesting scheme right from the first stage of execution, make it more economical, and the water obtaining can be used for the consideration purpose, for the construction purpose only. The rainwater harvesting systems can be incorporated with the landscape plan, and it can be used after that. The rainwater harvesting elements can be effectively used for the flood mitigation also. Now, whenever I'm doing the work, I have been asked, what is the cost? Let me tell you, the cost of rainwater harvesting system is maximum 0.5% of the entire construction cost, whereas cost of water requirement for construction is 4%. Using harvested rainwater saves 3.5% of construction costs. Since already used for construction, it is time tested until the building exists. It is free of cost. Stages. Study the project. Studying the project requirements, the research, site conditions, site features, site historical and proposed planning, studying the process development plan and the features, carrying out hydrogeological survey, dowsing rod method survey, pendulum and other surveys, discussion with the design team, processing the suitable rainwater harvesting system, and system takes time to mature, and once it does, then it's available for all throughout the life. Research. Rainwater harvesting schemes are site-specific. Besides the requirement of our project, the design is largely governed by important aspects like hydrology, soil science, topography, and climatological and geological factors. Now, this hydraulic cycle is very well known. The vaporization clouds and its form falls on the hill. And from hill, brooks, nalas, rivers, dams, and from there, we get the water today. Here, our job is to retain the water on the hills or elevated areas, percolate it, and increase the groundwater table, and not to allow it to go to the sea back again. The design. Rainwater water can be harvested in the following ways: rooftop storage and utilization, surface runout to be stored, surface runout to be recharged, borewell recharge, and other methods. Rooftop storage utilization. In the first job, when I started designing the building, which was at Bhose near Panjgani, it was at the highest location, but there was no water storage tank, nothing, no facility anywhere. So here I started thinking of collecting the water from the rooftop, and storing it into the ground tank, pumping it again, filtering it, and using it. But the water requirement was such, so this was not enough. So I thought of recycling it. Now, how much water you get? You take any area, length area into the average rainfall gives you the total water which can be collected on that land. With this basis, you can design the rainwater harvesting anywhere in the world. Now, in roof water harvesting, even if you construct a wall on the terrace, which is equal to the rainwater falling in the season, you can collect the total roof water. But its weight, its cost, its leakages. So this method is not adopted. But there is only one building which is constructed at Chandigarh, High Court building by Le Corbusier, is the famous example of roof water harvesting. The roof water can be collected from there into the tank next to it or under it. And care we have to take: no water storage below toilets, volume of underground water storage tank to be designed accordingly, no inspection chambers near underground water storage tanks, inspection chambers in RCC or CI with perfect waterproofing, rainwater pipes, inspection chambers should be away from the water storage tanks, and rainwater pipe not to be of 2 foot China ware socket pipes, but 20 feet heavy PVC pipes. Surface runoff. Now here, since I am based in Mumbai, I will explain you how I have done it in Mumbai. In Mumbai, the rainwater is generally 2,300 millimeters per season. Earlier, the Britishers had designed the water. 50% water will go by this rainwater or stormwater drainage, and 50% water will be percolating in the soil. But since Mumbai totally tarred or concretized, only 3% water is going inside the ground and 97% water is going to the sea. It's a sheer waste. Now, recharging at various geological locations. Now, Mumbai is an island city. There are 7 islands connected. 1/3 Mumbai is original, 2/3 Mumbai is constructed with excavated earth put there. So all the hills or all the islands are cut down and the soil is put in between two hills and connected. So when you work on the original ground mass, it's easier that you get the seed water. But where the land which is filled in, many times you get brackish water or salty water. But don't worry, when 3 years you continuously start harvesting the roof water or the rainwater, within 3 to 4 seasons, the water becomes clean and sweet. So even in the area which is filled, it is possible that you can get sweet water after 3 to 4 seasons. Now, how to put the water into the ground? We have deeper bore wells or ponds. Now, if you consider a bore well, a deeper earth crust to be harvested, on top of bore well, you can construct a bore and have a well on the mouth of it, put the water into the well after filtration, create a pressure and allow that ground mass below that in a conical form to be charged. This is the simple way of harvesting rainwater in the smallest area, in the urban area where the open space between the buildings is not even 10 feet. So this is the cost of this is in Indian rupees, maximum 2,50,000. But after this, you get lifetime free water, the water which is charged by you. Now, this is the plan of Mumbai, the original Mumbai with 7 islands. And this is the Mumbai which is constructed after cutting the hills of the islands and putting that soil in between the islands and connecting it. Now, when you are doing any harvesting in the area which is filled in, first you may have problem, but afterwards you start getting sweet water. This is the geological plan. I'll go further. This is what I was explaining to you. The original island, which you can see on the right hand side, original island, below that, you get sweet water very easily. But the refilled area, you have to have ring wells and put the water, rainwater, and charge it, and you get a sweet water. Now, this is the first project which I did, which I'm explaining you. You can see on the left-hand side top corner, the plot of land. This is undulating land. It is on the right-hand corner, it is the highest, and right-hand corner below is the lowest. Here, this is the real plan. Entire roof water is collected from the roof into the basements. Now, this land is sloping from left-hand top to the right-hand bottom. All these tanks are connected to each other. From the lowermost tank, the water is collected and taken up by the windmills. Then the stored water is either connected by solar or a cold water. So here in this, the 5 basic elements: earth, water, air, sun, and the earth, everything is used. And this building is there since 1995. Now, this is the section which is showing the tanks connected like this, and from the right-hand bottom, it is collected, taken up again, and stored. This is taken up by windmills, then it is stored. This is taken by through solar and cold water. This is used for bathing and cooking. This water is collected. This is filtered. This goes for the secondary use. That is for the flushing. Flushing water is again collected and filtered and used for plantation. This was not the thing. the best part was here I designed a small well, and this here in Mahabaleshwar, it rains 6,000 millimeters. So all these tanks are filled in 15 days. So what should I do? So I took all the excess water and put it into the well, and this hill, which was actually totally a devoted hill, where this water was put inside the hill was charged, and the best part of it, many villages down the line started getting the water. And that was the great thing happened. And because of that, the water scarcity in that area is reduced. This is another technical drawing which explains how the roof water is collected technically and into the tank and recycled again. These are the again part, the part water taken into the tanks. There are two valves. First is it's a first flush, taking the water out. After 7 days, again you stop it and take the water inside. We only use lime wash once a year before monsoon for cleaning the tanks, and that's all. There is nothing else is done, and it is working for last 26 years without any problem. Now that happens in a part like hill. Now this is in Ratnagiri districts where the laterite is there. Laterite stone is like a perforated stone. The water, when it rains, the water goes down. Here I only use plastic sheet, and I started collecting the water, and this is used there in various areas. Now here comes the urban solutions which I adopt. Here the roof water is first collected. Now this is the section. There are the refuse floors at every 8th floor. The roof water from the terrace water is collected into the tanks at every 8th floor where there are refuse floors. The water is stored into the tank, and then it overflows into the lower tank, and then finally it comes to the above the podium level. In the monsoon, cars get dirty. You need more water to clean the cars. So here the roof water is collected in various tanks and at various levels, and then used directly by gravity and by not by any electrical means or pumps to the lower floors, and it is collected at podium level and used for car washing in the monsoon. And this works so well. And also technically, when you are having water tanks at the upper level, even there is an earthquake, this helps to maintain the equilibrium or the balance, and it helps building design technically. There is one more example, that is this is near seashore. The seashore is here, and building is connecting the seashore, and there is a sand. The water from the roof was taken into the ground in a ring well. Now here, since it's a sandy area, there are no bore wells, but there are ring wells, and up to 6 meters there is sand, and you can store the water in that. What used to happen when I designed this system, the water used to get brackish during the high tide. So the excess water I started putting into the edge of the sea after filling up the tanks. And the thing happened that the water, these waves coming towards the building, they used to latch at the compound wall. But because of this, the water never got brackish again, and we are getting the water all the 12 months. More example, which one man award. This is near Andheri, SV Road and Western Railway. The land is sloping from SV Road to the Western Railway side. It's a blind home, and the water accumulation during monsoon, the blind children used to have problem in going out, and there was no water, and because of that, there was a lot of management problems. So and also that water used to go to the railway line, and the railway used to stop, and these people had to pay for that. Here, what I did, here I created a well. I percolated the water around the well inside the ground. See the next slide. In this manner, here is a well. There is a catchment area. Water was put down, so the water going to the railway line was stopped. The water accumulation in the compound was stopped. water started going inside the ground, and it gave them a source of water. Similar of Shipla near Vikroli, where again it is on the eastern side, and here also the water was going to the railway line. Here also it is stopped, and the funniest part is here. Here, when I was asked to do the rainwater harvesting, I started trying to place how to do it. I was told there are some old borewells which are dry now. I started excavating around that. I found, you can see the left-hand top photograph, which showing some borewells, which are shallow borewells, as per that technology, 50 and 80 feet. When I opened there, I found a well. We cleaned up the well and put all the water from that ground, from that property into this well, charge this well, and let me tell you, I'm getting more than 1 lakh liter water per day, and it's an industry. So industrial water is costly, and I could mitigate that problem with just harvested water from that property itself. Now, this is another prize-winning project at Oval Maidan. When Mumbai was developed, it was on the edge of the sea. The edge on the top side is the High Court building, and there was a Maidan, and the Britishers had done a perfect arrangement of taking the rainwater outside the ground in the monsoon. Okay, now that was taking the water in monsoon outside, and this, since it is a sandy zone, there was no accumulation of water. Here, a simple trick I played. What I did, I stopped the water going out, and then I constructed small ring wells, and I made the water to percolate inside the ground. Okay, and the last well was with the ring well system. Entire water, instead of going outside the property, it went into the ground. The water table was increased, and there are 8 wells, and all these 8 wells are giving water to the ground, and that water is one of the ground is one of the greenest grounds in Mumbai. This is Oval Maidan. These are the some of the photographs when the work was on. And just now, you must be reading in the papers, there is a lot of UN cry about rainwater harvesting of Shivaji Park. Now, this is one of the best localities in Mumbai, but the problem here today, the dust emission, and because of dust, all the property around, the people inhaling the dust, and they are getting TB and various other lung disease. So they went up to the chief minister and complained about it, and then it was decided that whatever the water which is falling on the ground and which is coming out of the ground is arrested. The red lines are showing that the water is arrested there and put it into the multi-ring wells. And these multi-ring wells are holding the water, and this water will be used all throughout the year for again watering, so that the dust emission is not there. Because of that, lawn grows up, and the problem of dust is solved. Also, the water is solved. Now, these are various very huge residential schemes. This is at Wadala. Wadala is on the edge of the island, and it is normally a sandy zone. So only ring well on the periphery are planned. Water, instead of going out, is halted and percolated into the ring wells all around. And this water is taken up to the monsoon, and it is being used for secondary use like flushing. This is one of the this is the MP Mill compound project, where the tallest skyscrapers are there in Mumbai today. Here, entire water from this plot of land is not allowed to go out. It was percolated in the soil. There are about 14 wells, and the water is percolated in the soil. And this area, they have no dearth of water for the secondary use. This is the industrial example where Dept Fertilizers in Gujarat. It is also near the sea, bang on the sea. Here the water is collected from the lowest area. It's pumped up into the lagoons. Each lagoon is of 50,000 meter cube capacity. There are 4 lagoons on the right hand bottom corner. This water is again used after the monsoon for the entire process of the factory, and this factory is working very smoothly for the entire year with this water, which is collected with the help of rainwater harvesting. Other methods. Now, this is slightly a rural method. This is the Jyoti Structures factory at near Ghoti. Here, it's on the hilly land. We have adopted each and every type of rainwater harvesting method here. On the top, it is trenching. With the trenching, the water is stopped at every level. There are small short bores. The water is put into the hilly area. At a lower level, there are bunds. At the lower level, lower than that, there are wells. And at the lowest level, there are ring wells. So water is not allowed to go out at all. And now this area is totally having on its own with the water harvested, and entire year this water is used. I'm always talking about water, but also in our use, we use electricity, electricity, which is made with the help of water only. But as an architect, when you plan a building, now if you go to any old mosque or a temple, you feel cooler. Why? Because the air is taken through a jali, of which the perforation is wider in the front and lower in the back. So the air gets compressed and you feel cool inside. I have constructed a building with similar principles at Hydropower. It's an industrial building where the temperature is reduced by this simple method by 6 degrees. And I don't have to use the fans. It's a factory. The workers never complain. And it was used for 20 years smoothly. This is the simple design of a jali. Also, if the building is ground plus 4, I design all the top floors by taking skylight. So on the upper floor, I don't have to take light, use our normal lights, electrical lights, but my top floor is always taken care with these roof lights above. So if the building is ground plus 3, my 25% electrical power is reduced. So here also, I am saving the hydraulic electricity. And this is the last example from my village areas. Here, in a simple building, they put plastic sheet and put cow dung and earth and have a lawn on top. And in my village where I stay, there is a lot of electrical problem. We have electrical shortage for 7, 8 hours, and it is unbearable to stay. Here, with this simple system, my structural means cooling is so much like an air conditioner. I don't have to use fan, and I can work with this without any problem. So if there is no problem, no electricity, there are no fans, yes, we can stay very comfortably. The benefits of rainwater harvesting is quality of groundwater improves, rises water levels in wells, bore wells, and that are drying up, mitigates the effects of drought and achieves drought proofing. An ideal solution for water problem in the areas having inadequate water resources, reduces the soil erosion as the surface runoff is reduced, choking of stormwater drains and flooding of the roads decreases, saving of energy and the life around ground and lift groundwater. 1 meter raise of water level saves about 0.4 kilowatt watt hour of electricity. And nowadays, I have taken up a problem, not only recycling, but reducing the use. I'm working on a scheme. In every house, we have this washing machines. Washing machine take more water. Washing machine takes more water. Normally, in water we use 145 liters per day per head. Out of that, 45 is for flushing and another 90 for domestic use. But if you save the water which is used for washing, if you have a small tank with which is designed to store this water after washing into a tank and use it for flushing. So your 1/3, 45 liters per day per head water used for flushing is saved. So you can save 1/3 water. You reduce your use of water. That can be used for another use. And I'm working on that kind of a design so that in future it should be possible for us to use the water for better use. Thank you.
Thank you, Mr. Mungekar. As always, your presentation is full of energy and passion for the work on rainwater harvesting that you have initiated. Indeed, I don't think that any architect has done as much work on this in this field as much as you have. Congratulations to you, and I see more projects that you have added in the last few years, and I'm sure there are many that you have not put here.
Yes.
And congratulations to you. There's one question here, and I also would like to ask. What is really interesting about your presentation is all the case studies that you have shared. So I think Anjali here is asking a question, and she says she's very impressed with your presentation and with your specific experience and knowledge. She also liked the long-term history of rainwater harvesting that you mentioned. Her question is that you mentioned about 3.5% of overall cost of a building. I think right in the beginning you mentioned this.
Yes.
So she's asking, is this related to a new construction or in average reconstruction, or is it for new construction? That's the question.
For any construction, reconstruction of a building or a normal building, for any, if you take construction cost today as 2,500 per square foot, the 4% cost is of water. 4% cost is of water. But if you do a harvesting system, it will cost you only 0.5%. So that water which is required for a building construction is available through that. So your 3.5% is saved. So it is for any type of construction. You harvest the water, you store it. In monsoon, the water flows out and meets the sea. Why? You just percolate it in the soil. Simple. And normal bore well, any bore costs is about 100 rupees per running foot. For 200 feet, 20,000. Pump 25,000. Ring well 50,000. In 2 lakhs rupees, you get permanent lifetime solution and permanent guaranteed water. What else you want?
Thank you. I just wanted to also ask you, since you have done so many projects, especially in Mumbai, what are the geological considerations
Yes.
that are required? I mean, do we need to have a geologist on board, or what important things do you do
Yes.
when you do a rainwater harvesting project?
Okay. That's a very, very nice question. Yes, geology and hydrogeology is the basic part of rainwater harvesting. That's why I explained you Mumbai, 7 islands. The main island, there was no problem. You can get the water. But when refilled area is the area where you have problems. Okay. Now, if you are in Mumbai also, there are sandy zones. If you go between Mahim to Prabhadevi, it's a sandy zone. More than 3,000 ring wells are there, and they are supplying the water to entire Mumbai. So wherever there is a sandy zone, there are ring wells. Whenever there is a basalt or the original part of land, you go for wells and bore wells. So this is the geological thing you have to take into account, and you have to plan the harvesting points. That's why in the opening thing I said hydrogeology and geology is the basic part one has to learn. I'm an architect, I'm a geologist also. I make use of all these things and I work with this. And also I use ancient methods, that is dowsing. Though I use all engineering methods, I'm more successful by using dowsing methods, which can be done without no cost, but 99% successfully. And that's why my schemes are very economical and cheaper, and I get success to the extent of 90%.
Can you explain us a little bit about dowsing? Or
okay, fine. I will just put on this. Yes. Now I will explain you that. Mother, okay. Now, can you see me? There are two rods. There are two rods here in my hand. These are dowsing rods. Okay. When I'm moving it, when they are going away, it shows there is no water. But if I move towards water, now see. When they stick in that direction, the water is there. Now, this is a simple dowsing technique anybody can do with any metal rods. I stand on four sides of the property, and then wherever these lines are cutting each other, that's a source or that's a area where there is water or a cavern, and exactly at that point I put my hydroresistivity meter. So the time spent is less, and my getting success is maximum, and which I check with my resistivity meter, and so I get a better result. Simple. And you can do this technique with the coconut also. You can do this technique with a shear douse, and you can definitely get the water. So along with engineering, you use this method. And whenever I go anywhere, and if somebody asks me, I just simply take a string and I tie a stone and I find out water. You can use that technique.
I remember hearing you earlier, your lectures, and you also mentioned some other means like, trees and all, which give you indication of the existence of water. Can you say a little bit about that?
Thanks for reminding me. Oh yes, very nice. I was not knowing how to compress the things in 1 hour. There are a lot of trees which indicate water. There are shlokas in Bhagavad Gita also, and lot of Indian shlokas where they tell you how to find the water. If you know this tree, which is called as Audumbar tree, which is available everywhere in Maharashtra or everywhere in India, on the north side of that tree, at 27 feet depth, you get the water. Blindfolded, you go there, excavate a well, you will get the water. The Jambul tree also indicates the water. Or wherever there is, white ant's house, what we call Vadu in Marathi. If you dig below that, there is water. So there are hundreds such points how you can find the water without knowing or without concerning geology or hydrogeology. But these are the indicators, okay, to find the water. And I have a book, I'm writing a book on this aspect, where one can find the water from the ground without having any hydrological or geological knowledge. And it is there, it is not mine. It is written in the shlokas.
Fantastic. I think we will all look forward to your book, all that knowledge that you have and all that knowledge that exists in our literature also.
Yes.
Just one last question maybe before I go ahead. You have given a lot of case studies in urban areas, but there are a lot of people in rural areas, and there are a lot of problems of shortages of water there. In urban areas, we generally get water in a tap, so it's easy for us, and therefore we don't realize the value of rainwater harvesting. But there's also a question here from Akshata, and that's also the question that I want to ask is, what kind of simple methods can be done for groundwater recharge or any other technique in rural areas, in rural, in villages?
Yes, that's what I tried to show on that Jyoti structures. All the methods like contour bunding. If there's a hill, you have contours all around the hill. Don't allow that water to slip down. Allow it to percolate. If the water is running, make it walk. If the water is walking, make it sit. If the water is sitting, make it slip and eat the fruit of that. You stop the speed of the water and its presence on the earth. Don't allow it to go to the sea. And that's the success. And do it by various methods. These are available since ages, since Ramayana. And we have to just practice them. That's all.
Thank you so much.
Thank you.
I now hand over back to Sneha for the next speaker. Thank you so much, Mr.
Thank
Mungekar.
you. Thank you.
Thank you, Architect Mungekar, and thank you, Doctor. I would like to introduce our speaker from Germany, Sanjali Berner. Anjali Butner is a graduate horticulture engineer from Department of Horticultural Sciences, Humboldt, University of Berlin, a practicing engineer and planner working with KLIMA Connection since 1994, primarily on green and blue infrastructure, landscape architecture, stormwater management, and spawn cities. She is also a lecturer on water management, engineering, ecology, and green infrastructures at the Bioth University since March of last year, and deputy professor in landscape architecture and green space management at the University of Applied Sciences in New Brandenburg, Germany. She has been involved in several prestigious international projects as expert landscape architect in Vietnam and Aquanet in Brandenburg. She was associate partner in Planner Resort, Berlin from 2005 to 2011 and CEO Butner Office on Garden and Landscape Planning till 2005. Among other important positions, she has worked with the Municipality of Berlin as leader of the Environmental Agency and Department of Parks. Anjali is certified expert in the trade union for rainwater management. She has more than 35 years of experience as an academician and environmental consultant. Over to you.
Hello, everybody. Good afternoon. I'm really glad to be here and to be together with my colleagues, which are absolutely experienced, and I'm absolutely inspired and amazed of that what I heard. So I have so many questions that the time won't be enough to ask them all, but eventually we can speak together later. This would be very nice. So today we have the World Water Day we're celebrating, and we all know what it means. My colleagues, you spoke about that, the different meaning in the different parts of the world. And in my lecture, I want to supply another view or another situation in Germany, especially Berlin. I now open my presentation. Can you see it all? Yeah, very nice. Thank you. So first, let me thank Roshni. Thank you and your team very much for invitation. I'm glad to be here and to speak a little bit about that, what I experienced in the last 35 years in Berlin and in other places. So let me start. My matter is water management in urban areas. I was already introduced, so I'm organized in different organizations.
Anjali, could you please put the presentation on slide more?
Sure.
I think it should be at the bottom.
Oops.
Yes.
Well, okay, welcome. So you already spoke about the climate change, and I don't want to go too global now. I want to come to Germany from the first moment on. We also meet the challenges of the climate change in a very hard way. Germany is one of the most influenced countries in the world by climate change. And for us, it means we also face floods and also face droughts. Actually, we are not at all as big as India, but in our relatively small country, in comparison to India, we also have extreme weather events. So our daily use of water, of tap water from population is approximately 100 liters per capita, so per person. And to provide the water, in Berlin especially, we use the most percentage of the water is groundwater for production of tap water. In other areas, they use more the lakes and the rivers, or also the dams. we've fought many years to bring the consumption of tap water down, because we had much more. Worldwide, it's between 25 and 300 liters. It depends from the country. In Germany, we are at around 100 liters. But it takes a lot of technology to produce this clean and very good tap water. And we are now facing the problems of the drought. I will come to that later. The extreme weather events are increasing. We have strong winds and storms. We also have stormwater events. We have increasing temperatures, less rain. We have overflows, which pollutes our rivers and channels. And also we have loss of groundwater and surface water. So our rivers and lakes lost water amount. Alone in Berlin, we can see it's 1 meter less in the water surface, which is really, really much. We have dying forests and trees everywhere in our parks and in our green spaces, which is really shocking and which causes other problems like biodiversity is going down. We have less insects and so on. And we have a strong erosion, as you can see on the right picture. But our aim in Berlin is to be climate neutral till 2050. Just a short graph about the temperatures in Germany. As you can see, they are strongly rising. We started with this measurements in 1960. The average temperatures was 8.4, and in 2020 we had 10.4, so 2 degrees more. And here's an example of precipitation in Berlin. We started with around 620, 30 in 1948. And with up and downs, we are now at under 500. When I started to work as an engineer and to plan rainwater management, we still counted, or we calculated with 550 to 600 millimeters per year. But this is long ago. And meanwhile, we have to calculate with under 500 here in Berlin. Another factor to plan and a basic for our development in Berlin is our canalization system. And dear Mr. Mungekar, you are a brilliant engineer. I saw that. And what you did, I was also, and I'm also doing the planning of the rainwater harvesting and the infiltration and the evaporation and all that stuff. And so the most interesting and most important thing are the soils, as you said, and as also Mr. Chopra, Dr. Chopra, and also Mr. Israeli said, we have our resources, and these are the soils, the water, climate, plus minus, and even ourselves as mankind. These are all resources, and we have to be really careful with it. And we here in Berlin worked about these resources already from around 18th century. So we have in my city, in Berlin, we have 2 different systems of canalization. The one is a combined sewer system, and the other one is a separate sewer system. So as you can see on the left side, I hope you can see it, in the combined sewer system, the two sewage, or the two waters come together, the rainwater and the wastewater from the households, from industry and so on. And all this goes together in one canalization. You can see the big tunnels. This is a canalization system. It's really old, but it's very well maintained. And this goes to the wastewater treatment plants of Berlin. And in the wastewater treatment plants, they clean it in different steps, and then it goes into the rivers when it's really clear, really clean. In the separate sewer system, which we started from around 1970, we have separated rainwater and sewage water pipelines. So you see one pipeline, the white one, is for rainwater. It also comes from the squares, the public spaces. It comes from the buildings, and it's a separate system for rainwater, and this goes into our rivers. And the other one comes from the buildings and so, and there we will find the sewage wastewater. And this again goes to the wastewater treatment plant. And the reason for that we have this, we started to build the separate sewer system, is that in the combined sewer system, we have a big problem. When we have a stormwater event, then rainwater and sewage go to the same system, like I told you, to the same pipelines. They go to the wastewater treatment plant. But if too much rainwater comes, the water can't flow fast enough to the wastewater treatment plant. And so there is a stop, and the water flows back in the pipelines and sometimes comes out of the shafts. And it comes out of an overflow system directly in our rivers. So our sewage, combined sewer system directly has an overflow into our channels and rivers in the city. And you can imagine what that means. That means we have a lot of sewage in our rivers. That means colibacteries and all of the other problems. And because of that, and because of climate change brings more and more stormwater events, our government in Berlin decided to build a new structure, and this is a separate sewer system. So more and more we are going on the way to build separate sewer systems for the rainwater system separated to the wastewater. So this is very important to know, because every planner, every architect, every landscape architect has to consider the site which he or she is planning about, and has to consider where are the pipelines, which canalization system is there, where are the shafts, how deep are the pipelines. This is a very important thing. Secondly, this system, because it caused many problems, many hygienic problems in Berlin. They started to say, okay, we have to maintain all the pipelines, and it should take some money. So our government founded a tariff system, developed a tariff system, and since 1st January of the year 2000, we have a splitted tariff system for rainwater. So every owner of a site, of a property, has to pay for bringing his rainwater into the public system. This is also very important because you can count and you can calculate these costs in your planning. So in your development of a rainwater or stormwater management project. These are very basic things we have in Berlin. Also, shortly, I show you the water household of Berlin. On the left side, we have the water household of open vegetation areas. We have a high percentage of evaporation and a smaller of infiltration. Here, the surface is covered by stones or something else like that. And we have a very high part of runoff. And the infiltration into the ground is very small. Also the evaporation. This is a household of Berlin. So we have a lot of evaporation. And this arrow goes to the combined sewer system. This one. And then into the rivers or into the soil. And on the right side, we have the water household of green roofs. And we have a huge evaporation. And a part of that goes into the canalization system. Actually, Berlin is still in a quite comfortable situation because we all think we have enough water. We have 6.5% of water surface of the whole surface in Berlin. We have 13 lakes and 360 kilometers of river shore. So we have a lot of water, but after the 3 very dry years, so 2018, 19 and 20, we lost a lot of water, as I told you. Mostly 1 meter is the difference in the surface of the rivers and lakes. So what did we do till today in Germany, and what is going on? We organized pay, so the tariffs for rainwater. People pay for tap water, wastewater. Also split money for irrigation water. We control the groundwater use, and we also control the overflow into rivers and channels. And we have a lot of water laws and rules. In technologies, we did a lot about stormwater management, so about infiltration, harvesting, evaporation, groundwater refill, and so on. We developed more green infrastructures. We created pump controls. We increased our maintenance of channels and rivers and the pipe system, and we also built combined water interim collection channels. So these are channels under the surface, at the moment around 300,000 cubic meters, which takes the mixed sewage and rainwater when there is a stormwater event to keep it away from the overflow into the rivers. Now, what I told you some minutes before. What we are also doing is in planning and education. We have national and regional plans for climate protection, environmental planning, and in all of that we follow the Sustainable Development Goals. This is very important. This goes through all institutions and has to be considered. And we also increase our environmental education for pupils, for young people, for everybody. We have a lot of publications We have also public lectures and workshops and so on. So we do a lot to integrate the people of Berlin and Germany at all. Now I come to one big plan and one big, yeah, how can I say? It's a kind of strategy. It's a strategy that Berlin will become a sponge city. Luckily, I heard Roshni, she told me that somebody in India said this should be kind of hocus pocus. I can understand these thoughts because to change a city into a sponge city means a lot of what has to be done. So I first speak about sponge city that Berlin plans for the hotter climate, which we have. And so how we can do it, I will explain now a little bit more. First, I must say it means the whole reconstruction of the whole city, because you have to change all surfaces into soft, open, breathing, water open surfaces. And this is a huge challenge, for sure. And especially in India, where you have other rainfalls, other stormwater events, it's another dimension you have to think. But I can explain you in several examples what can be done. Here are the first words, or the first what is to be done. So the methods are planting more trees, constructing sidewalks to provide shade, green roofs, green facades, light-colored buildings, heat-resisting road surfaces, urban wetlands, and changing of permeable surfaces into water-absorbing and storaging surfaces. These are some methods, and now I show you some examples what can be done. These are plannings which I did sometime before. This is a schoolyard and on a primary school. You can eventually you can imagine that this whole schoolyard was covered by concrete or other stones. There were only some benches for the kids, for the pupils, and some trees. Nothing real to play, nothing real to feel well, and so on. And then it was a challenge to make it more sustainable and to make it more to plan a better water management. So you can bring water from the roofs, as my colleague told you before, Mr. Mungekar. He spoke about water harvesting. In this case, I'm speaking about water harvesting and infiltration. And so we planned the schoolyard with a playground, and you can see the playground with the sand here in this area. But under the playground, I planned a trench pipe system, so the water can flow into these pockets, which can collect 95% rainwater. So the volume of the pockets is 95%. And when you have a stormwater event, the water flows into that one and then slowly infiltrates into the ground. Here you see some shafts. So these are pictures from the construction site. And then over the surface, you have a geotextile to avoid the soil from flowing into the pockets. And over the geotextile, there is sand, and in the sand, you have then a playground. You can see it here, a pump for the kids, and so they can play with the moist sand and can play with the water. And they have also an open, a little lake, a little pond, which is planted with some aqua plants. And yeah, so this is a school garden, yes. And they also grow some veggies and fruits in this garden, and they also have the pond. Another example is about facade greening, mixed with stormwater management and using rainwater for adiabatic cooling. So you see the structure of the building is quite interesting, and they planted different plants, climbing plants here. This is Wisteria sinensis, which was planted here. And the rainwater is used for cooling and for cooling of the rooms in the building. Another example, this is a so-called eco garden. This was planned and built in a very crowded district of Berlin, and this place was former only grassland, and then it became a ecological garden as an example what you can do in ecological planning and creating with such a piece of land. You can show the biodiversity, you can help the insects to live, you can plan a pond or build a pond and a bridge and a pergola and all of that. So this is a very nice place now for the pupils of the school, and they spend a lot of time in this garden. And you always have an open surface, so which collects water and infiltrates water into the ground, which is one part of the sponge city. Another example about rainwater harvesting, left side with a cistern and right side with a hollow trench system or trench pipe system. So the water comes from the roofs and goes into the trench pipe system and in the cistern, and is used for toilet flush and irrigation. This is done in a kindergarten. Another example, I hope you can see it. We have an entrance of a school, and there was a not so well planning, so that the water flows directly from the covered surfaces, from the stone surfaces into the school. You can see the water in the left picture above. You see the water in the schoolhouse. And so we planned a system to avoid that the water flows into the school. So we created such tunnels and a pipe system to bring the rainwater in this system and not into the school. Next one, this is a courtyard in Berlin. It was a European Union funded project, and this is also in the very crowded district of Berlin, Prenzlauer Berg. And also this courtyard was absolutely covered by concrete. And it was one task and 1/3 of the whole surface is over a cellar. So you can't really open the surface And because of that, we plant some high beds here. Plant beds and all the stones, all the pavement is water infiltrating. So it has bigger distances between the single stones, so the water can go through the stones into the ground. And a lot of facade greening and of plant beds and pergola and something like that. So you can change a full concrete space or place into a green and water breathing area. Another schoolyard, it was also full of concrete and stones, and it was changed in a landscape with some hills and a water basin, biological filter, and waterways, cistern for harvesting rainwater and for so used for toilet flush and irrigation. And it's also an educational project. This project was done together with the pupils of the school. They planned and they also realized it on the site. Another example is a public park. And if you plan a public park today, you should always consider the amount of rain which could come. So today, if you plan a public park, you should plan in different levels. So in different levels, it means you should plan like you have a low level where the water will stay when it's really dry in the season. When the water comes, it should raise up to a special level. You have to calculate that so that the people still can go around and can go their ways to work or to spend their free time with family or something like that. So you create different levels where the water can be stored in the open space. So this is the principle of Sponge City done in a public or in a private park. And such a park like here, this way should be, this goes around and also through the whole thing. And this way is on a higher level than the other areas. They are more down and they can collect water. When there's too much water after a stormwater event, it can be stored here. This is another example of one of our former airports in Berlin. This is a situation till now. So this is a big roof. Hello? Hello? It's very loud. This is a big roof, and all the water from the roof is flowing to a main pipeline, and then it goes into the into a big basin, and from there into a water channel of Berlin, but not into the surface, because we have a big green surface here. The planning now is they take also the water from the roof, bring it through the big pipeline, but then it goes by a pumping station, first into a big water basin, an open water surface, and then there is an overflow, and the overflow goes into the irrigation system of the park. So this is another example. We also have wetland roofs or also retention roofs. This is a special case now, which is also very nice for smaller smaller cities, or also for rural areas. You can do that everywhere in the world. You use the grey water and you use it for greening the roof, and you clean the water and you help the plants to grow by this one. You cool the air, and also you cool the rooms under the building, so around 8 to 10 degrees. Then we have to avoid big havaries or problems by the flood. We have precipitation possibilities. We have different software programs to precipitate, because they use the radar system, and so you can say 2 days, approximately 2 days before, when a stronger rainfall comes, and you can meet any possibilities to avoid distractions. Here, so we had a catchment scale, and we can then radar-based say how many water will come and which means should we take to avoid distractions and that things. Here's an example of grey water recycling in a passive house in combination with heat recovery. So that means you can use the water from a building. You also spoke about that, about grey water reuse, especially Mr. Israeli spoke about that. You can use the water for the heating system, and also to produce clean water. This is a combination of cleaning grey water and producing fish and plants, so vegetables. This is very amazing because the grey water comes from the different buildings around, and on the left side you see the different tanks where the grey water is cleaned, and then the cleaned grey water goes into other tanks with the fishes, and over the fishes are the vegetables growing, and they produce a lot of veggies. So this is a very nice combination. Mr. Israeli also spoke about wastewater treatment plants combined with constructed wetlands. This is very well known and very, very useful. It's not this what we do in Berlin, especially because we don't have so much space and we don't have those situations, but it's a very good example for other countries and also for other cities. It's very robust, and it takes only little costs and low energy. What is very necessary to say, and Dr. Chopra, you also mentioned that. I made a notice. I don't know if I find it now, but you spoke about that we all have to involve the people. We can't change our environment without people. People have to understand what is necessary, and especially now when we really have to change very, very fast our environment and our behavior and our production of energy and our using resources. We can't do that without the people. And so this is here is an example of participation. This is a schoolyard, and the planning was already made together with the pupils, and then we realized it together with them. So these blue water flows are made from the pupils. So a company built it, prepared it, and then the blue tiles were done by the pupils. And this is a lot of fun and a lot of amazing results, because people they feel a connection, a real emotional connection with this courtyard, with this schoolyard, and they always are proud. They show their parents, I built this. And yeah, this is a very important thing to involve the people. So I come to conclusion. I think, or I can imagine that even in India, you could start to rebuild cities into sponge cities. So by building rainwater collecting parks, removal of stone surfaces, improving infiltration, evaporation, and rainwater harvesting and storage, and so on. And you should make every surface green and breathing for water and for air, because we need green surfaces. Only the green is a buffer for temperature, for moisture, and also for CO2. And this is what we have to do next. And yeah, I hope we can work together anyhow to make our world greener and more resistant against the climate change. And I'm really lucky to have all of you with me here on in this conference, and like to come into an exchange of knowledge and experience. And now, with greetings from Berlin, I say goodbye and thanks for attention. Thank you.
Thank you, Anjali, for this wonderful presentation. I'm sure that the audience and the participants now have a very clear idea of what green and blue infrastructure is and what sponge cities are. And, and thank you for sharing these case studies, which really made it so very interesting, because we saw what you have done in action, especially what you have done in cities. In the schools, sorry, it's really amazing that you transform these, concrete surfaces. I just remembered that maybe last year or year before last, I had written an article in the newspaper here when there were, again, intense floods, and people were asking why there is so much flooding, in areas where it never flooded before. And the reason was very simple, that in the city of Mumbai, we do mostly redevelopment. And when they do redevelopment, they completely concretize the surfaces. And they want more and more parking, and that's all they think about. There's hardly any surface open for the water to percolate. And then, the water simply gets onto the streets, it goes into the storm water. It's overwhelming amount of water that comes in. So the work that you're doing is truly amazing. And that's, I'm so glad that you have spoken just after Mr. Mungekar, who is also doing similar kind of work. And I think both of you share the same passion for this kind of work. Thank you so much. Let me see if there are, there was a very general question, which I will ask, which Rohan has asked about. Professor Rohan Gurav asked, what are the recent strategic plans Berlin government has initiated for year 2020-2021 with respect to environmental protection?
This is a big question. I know some answers, but it's not easy to bring it into a short answer. As I told you, we have different plans. We have an German-wide plan, and we have Berlin-wide plans. We have a so-called Green Charter, and the Green Charter is a guideline what we want to do in the next years, and especially, okay, the year 2020 is over. I speak now about 2021, and in 2021 we will have a very important thing. We will have elections, even in Berlin. And this always means, first, after election, there is a kind of break in doing, because all the politicians first have to sort out who is cooperating, who is making, how to say, you know, which party goes with the other one, which with which one, and so. So with the collaboration planning takes some time. This is first point. And then it's really important which party is winning the elections. Because I think you also have conservative and more progressive parties, and this means they have different election programs or different programs for the future. And what I can say in Berlin, so the green or progressive parties really fight for or fight against the fuel, so the fuels for the cars. It shouldn't be benzene. Oh my God, my head. Sorry. So the normal cars today, they drive by gas or by gasoline, you know. And this we want to change into renewable energy to use it for the cars. This is one aim, so this is very important. Then the second one, we will become a climate neutral city till 2050, and this for that we did a lot of specified plans. We have one plan, this is called STEP. This means it's a plan of climate protection methods and steps. Yeah. So in there we have really specific and very exactly the different steps to become climate neutral and to become a blue-green city and to become a sponge city, and all of that. We have a lot of have a lot of plans. Then there's a question about the 3 major economic challenges. I'm not a politician, but I want to answer that firstly, Corona changed a lot. I think also in your country. We are facing a lot of challenges because of Corona, because our small and medium enterprises have a hard time the whole year long already in 2020. And they have to become more strong again after or in between of Corona. This is a very important point because many of our companies already gave up. They can't do their business anymore. So this is a special thing. But another thing is we have to rebuild our car production and change it from non-renewable energy to e-cars and also H2 cars or hybrid. So this is a big challenge. we want to ban the non-renewable energies out of the city. We want to use more renewable energies like wind energy, PV, water power, not so much, but PV and wind is the most thing.
In terms of your work that of spawned cities and green blue infrastructure, is this something that is generally practiced by a lot of landscape architects, or is this a very niche area that you're working in, or is there some kind of a policy support for you, or do you face a lot of obstacles, or do you have to convince clients or schools that you've worked with that you need to do this and it was very difficult? How does it happen? This is what I would like to know.
Yeah, actually, when I started with my profession, it was like a pioneer's work, because rainwater wasn't considered at all. No, it was, we had this canalization system and all was working very well. Yeah. And in 1996, when I did my first planning of rainwater management, it was an ecological thinking and an ecological duty, which I felt. But step by step, and together with other colleagues, the matter of rainwater and of greening became more and more well known in the municipality, the government. We worked a lot for that. You know, we did a lot. We did a lot of lectures, of conferences, of workshops, all of that in every municipality. So it took a long time, and a very big or very important step was to get this tax or this tariff for the rainwater, because from this moment on, in the year 2000, we had an instrument for calculation. We could say to an owner of a private property or to a school director, we could say, okay, you now, for instance, in one of the schools I planned, they pay in every school till now, they pay around 10 to 15,000 euro per year only for the rainwater runoff into the system. Yeah, it's a lot of money, and this is an economic angle. You know, you can calculate and you can say, okay, we invest, I don't know, 150,000. You pay 15,000, so after 10 years around, we have a return of investment. Yeah, this was very important. Meanwhile, we have, by our work, it's quite normal for landscape architects to plan, not really with the blue, because this is a special knowledge. In many cases, they have a hydrologist or an environmental engineer, and they cooperate with them. It depends how big the office is, if they collaborate with other specialists. But the thinking about blue and green is very normal in between, because also our politicians did a lot, and we have a lot of plans. How I told you, step by step, we want to develop our city into a green and a sponge city. So it's quite normal in between, and we also have funds in Berlin to, for instance, we have a fund for greening roofs. They don't pay the whole price, but an amount, a part of the costs they pay. This is one example.
Okay. So this is paid by the government.
Yeah.
Fantastic. Fantastic.
Yeah. Yeah.
Yes, it's a sort of incentive and it's also awareness, because then the government is sending a message that greening a roof is important.
Yeah, yes, absolutely. It's more the question of organizing such a program that it really works, because we have mixed ownerships in Berlin, a lot of mixed ownerships, and then it's not easy to do a roof greening because all the owners have to agree, and some of them don't want. They say, oh no, I don't want to invest, even though the government is paying some money, so not so easy.
Just one last question, maybe before we wind up for today. There's a question from Shruti, who is a student, who wants to know, are there new areas of research in this field that you could suggest that she or her class or students could take up?
What a question. There is so much going on. They research in all areas of water, in all really, about wastewater management, about grey water. We started a new research program or project about using grey water for reuse in the cities for irrigation. We have special technologies to bring rainwater directly to tree roots. We have more research in drink water use and drink water providing. We have a lot of research. So if he or she is interested, he can or she can send me an email and we can stay in contact if I can help.
Okay. So I don't see any more questions. No, there is one. Could you please share their presentations? This is something I think Mr. Mungekar is here, Mr. Dr.
Yes.
Ravi is here, and Anjali is here. There are some questions that the students are asking if we can share the presentations.
Sound?
Sure.
Maybe we can ask the speakers offline and send it to them. Whoever wants to share, okay, we can send it to the students. That is possible. Yes.
Yeah,
Roshni,
I would like.
Yes, I think Mr. Dr. Ravi is here. Yes.
Roshni,
Yes.
I can send you. You have the presentation, right?
Yes, I do. Yes.
What I showed today was a slightly edited version of what I sent you yesterday.
Okay.
So I can send you the new version and you can pass it on to whoever wants it.
Great, great. I'll
Okay.
do that. Yes. Thank you. Okay. I think we can ask the other speakers as well offline, and then we can send it to you. This was a message from Mr. Kukreja, Johan Kukreja. Okay, so I think we have almost come to the end of our symposium of today with two international speakers and two very eminent national speakers who all these speakers were absolutely superb in the amount of knowledge that they shared with us, the case studies and the examples, and starting from Dr. Ravi, who gave us a whole spectrum of what is happening in the Himalayan rivers and what we need to do, also the solutions. We had Mr. Abraham, who showed us about the technologies in Israel and what a small country like that can do and what we can do by following them. Mr. Mungekar has shown us rainwater harvesting right from our traditional past to the case studies that are there today. And Anjali has enlightened us about what she is doing in Berlin and what Berlin itself is trying to do in order to improve the city environment. So I want to thank all the speakers today. I think it was a fantastic session. We will be, of course, sharing the YouTube version of this entire symposium so that anybody who missed any part can watch it. It will be available as a repository of knowledge for everyone here as well as anywhere else. Thank you very much, and I hand over to Sneha.
Thank you, Roshnima. Thank you, Anjali. I would now like to thank all our speakers on behalf of the Institute for giving your valuable time and sharing your expertise with all our participants. I thank Dr. Ravi Chopra for sharing his knowledge on the North Indian water resources and other elements. Thank you, Mr. Evram Israeli, for the wonderful presentation on Israel's water challenges and the drip irrigation techniques as well. Thank you, architect Nandan Mungekar, for sharing your projects and your ideas on rainwater harvesting and related issues. I thank Anjali Bhatna for your knowledge on the German water harvesting systems and more. I express my sincere thanks to Dr. Anand Shivapur, Chairperson, Department of Civil Engineering, VTU, Belgaum, and Organizing Chairperson of the today's program. I also extend my thanks to Professor Rohan Gurav, the Assistant Professor for Department of Civil Engineering, VTU, for coordinating this event at VTU. As you can see on the slides, here are a few of our VTU students from Belagavi and Gulbarga, Belgaum, Karnataka. It's a matter of immense pride for me to convey my gratitude to Honorable Vice Chancellor, Dr. Karisidappa VTU, Belagavi, Government of Karnataka, India, Registrar, Dr. A.S. Deshpande, VTU Belagavi, Government of Karnataka, India, for their constant support and encouragement during this program. I also extend my heartfelt thanks to VTU officials, course coordinators, faculty members, PG studies of VTU Belagavi, and all the students of VTU. I'd also like to thank our IEAR President, Dr. Roshni Yoda, for organizing this successful international symposium. I thank our Vice President, IEAR, Architect Rajiv Tashete, Treasurer, Dr. Shashidhar Kashyap, our Secretary, Dr. Advocate Sadhna Mahashabde, and all our team members and trustees of IEAR for their support and encouragement. Thank you one, thank you all. Lastly, please fill the feedback form to receive your e-certificate. Please note the link will be activated only till 5:30 today. I would like to inform all our viewers that there will be a hands-on one-day field trip workshop on watershed management and groundwater recharge on the 24th of April 2021 in Alibag, the details of which are displayed on the screen for you. We would like to thank all who are a part of our virtual family on Instagram and Facebook and are making us stronger with your support. If you aren't yet a part, do follow our Instagram and Facebook page for further updates. The link to join our pages have been posted in the chat window. Also subscribe to our YouTube page and do check our past webinars. We have covered 19 webinars till now on varied topics. Thank you all for joining today. Take care and stay safe. Bye.
Bye.